Welcome. Tonight we are going to do something unusual. We're going to slow down. Not in the way you slow down when you are tired, or the way a song slows toward its final note, or the way a conversation tapers into comfortable silence. We're going to slow down in a much more fundamental way. We're going to adjust the clock by which we measure events, stretching it from the human scale, from the scale of heartbeats and seasons and lifetimes, all the way out to the scale at which the universe conducts most of its most important business. We're going to spend 3 hours together exploring the slowest things in existence. Not the slowest objects, though we will encounter those too. We're going to explore the slowest processes, the transformations that are happening right now, all around you, beneath your feet and above your head and inside the atoms of your own body, that are so gradual, so patient, so utterly indifferent to the brief flickering of a human life that you could watch for 1,000 years and see nothing change at all. The drift of the continents beneath your feet, the erosion of mountains that once stood taller than the Himalayas and are now nothing but the low rolling hills of ancient continents, the evolution of species across millions of generations, the slow cooling of the Earth's interior, a fire that has been burning since before the sun existed and that will not go out for billions of years to come. The migration of stars through the galaxy on orbits that take hundreds of millions of years to complete. The expansion of space itself, carrying the most distant galaxies away from us at speeds proportional to their distance, silently, constantly, without any force or explosion, simply because space is growing. And slower still, the evaporation of black holes, emitting particles one by one over timescales that make the current age of the universe look like a single tick of a cosmic clock. The possible decay of protons, the building blocks of matter itself, dissolving so slowly that we have been watching tanks of pure water deep underground for decades without witnessing a single event. And slowest of all, the heat death of the universe. The final, ultimate, most patient process of all, the approach of the entire cosmos toward thermodynamic equilibrium, toward the state of maximum entropy, toward the condition in which nothing more can ever happen, which is still so far in the future that no unit of time we currently use comes anywhere close to describing the distance. These are the things we will explore tonight, together, slowly, in the dark, and I want you to notice something as we go, something I think is one of the most quietly astonishing things that the study of these slow processes reveals. Slowness is not inactivity. The things we will discuss tonight are not things that are failing to happen. They are happening right now, with perfect consistency, with absolute physical inevitability. The continent you're sitting on is moving as you listen to these words. It has not paused for this narration. The mountains outside, wherever you are being worn down grain by grain, even as you breathe. The protons in your body may be decaying so slowly that the universe will end before you lose a measurable fraction of them. But if the physics is right, the process is underway. The universe does not notice your sense of urgency. It does not share your impression that things should happen on a human schedule. It has its own schedule, written in the language of physics, and it keeps that schedule with a precision and a patience that nothing we have ever built or imagined comes close to matching. Tonight, we learn to read that schedule. Tonight, we learn to be slow. Before we begin, if you're enjoying these long journeys into the quiet science of deep time and deep space, please take a moment to like this video and subscribe. It costs you nothing but a gesture, and it means more than I can easily say to those of us who make these things, who sit in quiet rooms trying to find words for processes that unfolded before words existed and will continue long after the last word has been spoken. And leave a comment. Tell me where in the world you are right now. Tell me what time it is and what the weather is doing outside your window. And whether you're somewhere familiar and comfortable or somewhere new and slightly disorienting, I read every comment, and I find the geography of these listeners scattered across the planet, each one lying in their own darkness, thinking about the same slow universe, deeply moving in a way that is difficult to articulate, but that I feel every time I read through them. You are all of you sitting on a continental plate that is moving. You are all of you breathing air that was exhaled by ancient oceans and ancient forests and ancient creatures whose names we do not know. You are all, every one of you, a brief and improbable arrangement of atoms that will eventually, slowly, and inevitably become something else. And tonight, together, we're going to sit with the slowness of all of that. We're going to let the universe's timescale wash over us. We're going to let the pace of geology and astronomy and thermodynamics set the rhythm of the next 3 hours. Take a breath, a slow one. Let your body settle, and let us begin. Before we descend into the first of tonight's slow processes, let us take care of a few practical things. Find your most comfortable position, the one where your body does not need to shift or adjust, where the weight of the blanket or the warmth of the room or the firmness of the surface beneath you is exactly right, where you could stay without moving for a long time. Tonight especially, I want you to settle into stillness, because we're going to be talking about processes that operate on timescales so vast that human lifetime is invisible within them. And to really feel that, to really let it land, you need to be still. You need to let the ordinary urgency of the body, the restlessness, the small fidgets and adjustments quiet down. Give yourself permission to be motionless. Dim the lights, or turn them off entirely. Darkness makes slow things feel slower in the best possible way. It removes the visual noise of the room, the objects and surfaces that anchor you to the particular moment and the particular place. And it opens something in the mind, a kind of spaciousness that makes it easier to think on scales much larger than the immediate. If you have a fan running, or the sound of rain, or the white noise of city at night, drifting in through a window, let those sounds be present. They're good company for this kind of journey. They create a kind of acoustic envelope around you, a soft separation between the inside of this narration and the outside world. And take one more breath. Notice, if you can, that the oxygen in that breath was produced by photosynthesis in plants and phytoplankton, a process that has been running on this planet for roughly 3 billion years. Notice that the nitrogen that makes up most of what you inhaled was cycled through the atmosphere and the soil and the bodies of living things over geological timescales stretching back billions of years. Notice that the carbon dioxide you exhale will eventually, over millions of years, become part of limestone on the ocean floor, or part of the body of a future organism, or part of a future atmosphere on a future Earth that neither you nor anyone you will ever meet will live to see. You're already part of the slow processes. You always have been. Now, let us go meet the rest of them. There's a particular kind of intellectual vertigo that comes from trying to genuinely hold geological or astronomical timescales in the mind alongside human ones. Not just to know the numbers, which is easy, but to feel the relationship between them, to have some visceral, intuitive sense of how human time and deep time relate to each other. Here is one way to approach it. The oldest living organism whose age we can verify with certainty is a Great Basin bristlecone pine tree in the White Mountains of California, named Methuselah, which is approximately 5,000 years old. 5,000 years is already more than the entirety of recorded human history. Methuselah was a mature tree when the pyramids of Giza were being built. It was ancient when Rome was founded. It is still alive, still growing, still producing pine cones and seeds in the same mountainside where it germinated from a tiny seed sometime around the year 3000 BCE. 5,000 years. That is a long time for a human mind to contemplate. And yet 5,000 years is to the age of the Earth as approximately 1 1/3 seconds is to a full year. If you compress the entire history of the Earth into a single calendar year, with the formation of the planet occurring at the first stroke of midnight on January 1st, then Methuselah would have germinated approximately 12 milliseconds before midnight on December 31st. The entirety of recorded human civilization would fit in the last few seconds of a year. And the Earth itself, 4.5 billion years old, is not even the oldest thing we will discuss tonight. Some of the processes we will explore operate on timescales that make the age of the Earth look brief. The evaporation of the largest black holes will take 10 to the 106th years, a number that makes the age of the universe, itself already 13.8 billion years, look like the first tick of a clock that will run for a time beyond any meaningful description. Tonight, we will visit all of these timescales. We will move between them as freely as we can, using analogy and image and the slow rhythm of narration to try to bridge the gap between the human scale and the cosmic one. It will not always be comfortable. The mind resists scales it cannot intuitively grasp. But that resistance, that slight vertigo, that sense of being stretched gently beyond ordinary comprehension is part of what makes this kind of exploration valuable. It loosens something. It makes the world feel larger and older and stranger and more full of patient wonder than the ordinary day allows. That is precisely where we want to be tonight. Right now, as you lie still, as your body rests against whatever surface supports it, the ground beneath you is moving, not shaking, not shifting in any way you could detect with any instrument you own or any sensation your body is capable of registering. Moving smoothly, continuously, silently, in a direction determined by the slow convection of the rock beneath it, at a speed that varies depending on which tectonic plate you happen to be resting on, but that averages somewhere between 2 and 15 centimeters per year. 2 centimeters per year, the width of your thumbnail. That is how far the ground beneath you will have moved by this time next year. And yet, in the fullness of geological time, that 2 centimeters per year is enough to have moved continents halfway around the world, to have opened and closed entire oceans, to have built the highest mountain ranges on the planet, and then worn them down to nothing and then built new ones from the rubble, to have rearranged the entire surface of the Earth so thoroughly and so repeatedly that a map of the world 200 million years ago would be unrecognizable to any modern eye. 2 centimeters per year, and it changes everything. The idea that the continents move, that the vast land masses of the Earth are not fixed in place, but are instead the slowly drifting passengers on a set of rigid plates floating on the viscous rock of the mantle below, is so thoroughly established today that it is difficult to remember how recently it was considered not merely wrong, but absurd. The kind of idea that gets a scientist laughed out of a conference room. The man who first proposed it seriously, with evidence and argument and the willingness to be publicly mocked for it, was a German meteorologist and polar explorer named Alfred Wegener. In 1912, Wegener published a paper, and then in 1915 a book, presenting the hypothesis of continental drift. He noticed what many others had noticed before him, that the coastlines of Africa and South America fit together with suspicious precision, like two pieces of a jigsaw puzzle that had been pulled apart. He noticed that identical fossils of the same extinct species were found on opposite sides of the Atlantic Ocean, in places that were now separated by thousands of kilometers of open water. He noticed that geological formations, rock types, and mountain chains matched up across continents that were now far apart, as if they had once been parts of the same continuous structure that had been broken and separated. From all of this evidence, Wegener concluded that the continents had once been joined together in a single supercontinent, which he called Pangaea, from the Greek for all lands, and that they had since drifted apart to their current positions. The geological establishment of the early 20th century rejected this idea almost universally. Not because the evidence was bad, though critics raised legitimate questions about some of it, but primarily because Wegener could not propose a plausible physical mechanism for continental drift. How could a continent move? What force was strong enough to push a landmass the size of Africa across an ocean? The rocks beneath the continents were solid. You could not push a continent through solid rock. The idea seemed physically impossible. Wegener died in 1930 on a rescue mission to a stranded expedition in Greenland. Still largely dismissed by the mainstream of geology, his central insight unconfirmed. He did not live to see his vindication. That vindication came in the 1950s and 1960s with the exploration of the ocean floor. As oceanographers mapped the seafloor with increasing precision, they discovered something remarkable. Beneath the oceans, running for tens of thousands of kilometers through every ocean basin on Earth, was a continuous system of underwater mountain ranges, mid-ocean ridges, and at the center of these ridges, running along their crests, were long valleys from which fresh volcanic rock was continuously being extruded. The seafloor was being created at the ridges. New rock was being added continuously, pushing the existing seafloor outward on both sides. And if the seafloor was being created at the ridges, it must be being destroyed somewhere else because the Earth is not growing. The answer was found at the deep ocean trenches, the subduction zones, where one plate of oceanic crust dives beneath another and is pulled back down into the mantle, melted, and recycled. The mechanism Wegener had been unable to identify was the convection of the mantle itself. The rock of the mantle, while solid on human timescales, behaves as a very slowly flowing fluid on geological timescales. Hot rock rises from the deep mantle, spreads outward beneath the lithosphere, and eventually cools and sinks again in great convective cells that move on timescales of millions of years. The tectonic plates are carried along on this slow mantle conveyor, moved by a combination of the push of new material at the ridges and the pull of the cold, dense, subducting plates at the trenches. Wegener was right. The continents move. The Earth has a mobile surface, unlike any other planet we have yet observed. And that mobility has shaped everything about the world we live in, from the distribution of the continents and oceans to the climate to the evolution of life itself. Let us travel back, not far by cosmological standards, but far enough that the world would be completely unrecognizable. 250 million years ago, the Permian period, just at the boundary with the Triassic, the moment of the greatest mass extinction in the history of complex animal life, when perhaps 96% of all marine species and 70% of all terrestrial vertebrate species were wiped out in an event that took millions of years to fully play out. At this moment in time, the Earth's land masses are almost entirely consolidated into a single supercontinent, Pangaea, stretching from pole to pole, occupying roughly a third of the Earth's surface, surrounded on all sides by a single vast ocean called Panthalassa, the ancestor of the modern Pacific. The interior of Pangaea is a continent of extremes. Far from any ocean, the climate of the interior is harsh and dry, a vast continental desert where temperature swings between seasons are more extreme than anything experienced on modern Earth. The coasts are lush, warmed by the shallow seas of the Tethys Ocean, a great embayment in the eastern side of Pangaea that will eventually become the Mediterranean Sea and the Indian Ocean. Now imagine standing somewhere in the middle of what will eventually become the Atlantic Ocean, 250 million years ago. There is no ocean here. You are standing on dry land, a broad, flat lowland between the mountain ranges that will eventually become the Appalachians of eastern North America and the Atlas Mountains of northwestern Africa. Those mountain ranges are part of the same continuous belt of ancient collision mountains, built when the ancestors of North America and Africa crashed together hundreds of millions of years earlier, and are now being slowly eroded by wind and rain. Under your feet, far below the surface, the mantle is convecting. Hot rock is rising. The crust is being stretched and thinned. Cracks are forming. Within a few million years, rifting will begin. The crust will split. Lava will pour into the growing rift valley. And then, as the rift deepens, seawater will flood in, and the embryonic Atlantic Ocean will be born. From nothing to an ocean in a mere 50 million years. 50 million years. It sounds like a long time, and by human standards, it is an incomprehensible span of time, stretching back further than the extinction of the dinosaurs, further back than the first grasses, further than the first flowering plants, back to a world that looked nothing like the one we know. But by geological standards, 50 million years is a relatively brisk transition. The Atlantic opened quickly, as continental rifts go, and it has been widening ever since at a rate of roughly 2 to 3 centimeters per year. In the time it takes you to finish this sentence, the Atlantic will have widened by approximately the thickness of a human hair. By morning, it will be measurably wider than it was when you lay down. Right now, the Earth's surface is divided into approximately 15 major tectonic plates and a larger number of smaller ones, all moving in different directions at slightly different speeds, driven by the mantle convection below and by their own weight at the subduction zones. Each plate is a rigid slab of rock, typically between 50 and 200 kilometers thick, comprising both the crust at the surface and the uppermost, cooler, more rigid part of the mantle below it. Together, these plates make up the lithosphere, the outer shell of the Earth. The fastest moving plate is the Australian plate, which is moving northward and slightly eastward at approximately 7 centimeters per year. Australia, as a result, is slowly colliding with the islands and seafloor of Southeast Asia, a collision that will, over the next tens of millions of years, build new mountain ranges and eventually weld Australia to Asia in a new configuration of the continents. The Indian Plate, having separated from Antarctica approximately 130 million years ago and having moved northward with extraordinary speed for a tectonic plate at rates of up to 20 centimeters per year during its period of fastest motion, collided with Asia roughly 50 to 55 million years ago. That collision is still ongoing. The Himalayas and the Tibetan Plateau, the highest mountain range and the highest plateau on Earth, are the crumpled, thickened crust of a zone where India and Asia are still pressing against each other. The Himalayas are not a relic of an ancient collision. They're a living, active, growing structure. Mount Everest is getting very slightly taller every year, by approximately 4 millimeters, as the Indian Plate continues to push beneath Asia. The erosion by glaciers and rivers is wearing it down at roughly the same rate, which is why it has not grown to an impossible height. The mountain is in a slow balance between the force that builds it and the forces that destroy it. Beneath the Pacific Ocean, the Pacific Plate is moving northwestward, diving beneath Japan and Alaska and the Aleutian Islands along its northern edge, and beneath the west coast of South America along its eastern edge, generating the volcanoes and earthquakes of the Pacific Ring of Fire. Every earthquake in Japan, every eruption in the Cascades of the American Northwest, every tsunami generated in the deep trenches of the Western Pacific is a consequence of this slow, relentless tectonic motion. Under the Atlantic, the Mid-Atlantic Ridge is spreading. Europe and North America are moving apart at roughly 2.5 centimeters per year. Iceland, sitting directly on the mid-Atlantic ridge, is one of the few places on Earth where a mid-ocean spreading center emerges above sea level, and is slowly being pulled apart as the two sides of the ridge move away from each other. Lava erupts along the ridge, adding new material to both plates, slowly widening the island. And beneath Africa, a new rifting event is underway. The East African Rift System, stretching from the Afar Triangle in Ethiopia down through Kenya and Tanzania and into Mozambique, is the embryonic stage of a continental rift that, given enough time, will split the eastern part of Africa away from the rest and open a new ocean between them. In tens of millions of years, the Horn of Africa and the region east of the rift will be a separate island continent, moving away from the rest of Africa across the widening waters of a new ocean. None of this is visible in a human lifetime. None of this is perceptible to any sense you possess. It happens beneath you continuously at the pace of fingernail growth in the deep quiet of the geological timescale. And yet it is one of the most consequential processes on Earth. It builds mountains and opens oceans and creates the islands and coastlines and geological features that shape every aspect of the physical environment. It cycles carbon between the atmosphere and the deep Earth, regulating the climate over millions of years. It creates the conditions for biodiversity by separating populations of organisms onto different continents and allowing them to evolve independently. It is, in a very real sense, the engine of the living world. All of it moving at 2 centimeters per year. Let us move forward in time now, not backward to Pangea, but forward into the deep future of the continents, the world that the current motion of the plates will eventually produce if it continues at its present pace. In approximately 10 to 50 million years, the East African Rift will have widened enough to be flooded by the sea. A new ocean basin will be born. The land that is now Ethiopia and Somalia and Kenya will begin to separate from the rest of Africa. Species populations that are currently continuous will be isolated by the new seaway, and evolution will proceed independently on either side, producing new species, new ecosystems, new biological communities that could not have been predicted from the current distribution of life. In approximately 50 million years, Australia will have completed its northward journey and will be colliding with Southeast Asia. New mountain ranges will be rising along the collision zone. The geography of the Pacific will have changed substantially, with the Indonesian archipelago compressed and uplifted by the advancing Australian plate. In approximately 50 million years, the Mediterranean Sea will have closed. Africa and Europe will have fully collided, the remnant Tethys Ocean crushed between them. New mountain ranges will have risen along the collision zone, higher than the Alps. The sea that Cleopatra sailed on, and that the Roman Empire bordered, and that has been central to the history of human civilization will be gone, transformed into a mountain range. In approximately 250 million years, in a scenario that geologists call Pangea Ultima, or Nova Pangea, or Amasia, depending on the specific model, the continents will once again be assembled into a new supercontinent. The Atlantic will close as the Americas drift back toward Europe and Africa. The Pacific will continue to shrink. The world will have a single vast landmass again and a single vast ocean, and the geography of life will be reset once again to a condition that no creature alive today would recognize. And then, in another 250 million years, or perhaps sooner, the new supercontinent will begin to rift apart again, because that is what supercontinents do. They accumulate heat from the mantle beneath them, because they act as thermal insulators, preventing the heat from escaping. The trapped heat eventually causes the mantle below to swell and the crust above to crack, and the rifting begins again, and the slow dance of the plates continues, as it has for at least 3 billion years, and will continue for as long as the Earth retains enough internal heat to drive mantle convection. The Earth is a restless planet. Its surface is never finished, never settled, never done rearranging itself. It will continue to move, to build, to destroy, to rebuild, long after the last human has drawn their last breath, long after every trace of every civilization has been buried under kilometers of sediment or subducted into the mantle or eroded into the sea. The plates do not need us. They do not know we are here. They were moving before the first cell divided in the primordial ocean, and they will be moving after the last complex organism dies. And right now, as you breathe, as your heart beats, as your thoughts form and dissolve in the quiet dark, they are moving 2 centimeters per year, 1 breath at a time, unstoppable, patient, permanent. Let that settle into you as we move to the next of tonight's slow processes. The mountains that the moving plates build, and an even slower process by which those mountains are quietly, grain by grain, returned to the sea. There is a mountain range in Scotland called the Caledonian Mountains, or rather, there was. What remains of them today are the Scottish Highlands, the ancient, rounded, heather-covered hills that rise above the lochs and glens of northern Scotland, beloved by walkers and painters, and anyone who has ever stood on a high ridge in cold wind and felt the peculiar combination of smallness and expansion that high places tend to produce. They are beautiful. They are old. They feel permanent in the way that only large pieces of rock can feel permanent, as though they have always been there and always will be. They have not always been there, and they will not always be. 420 million years ago, the Caledonian Mountains were new. They had just been built by the collision of 2 ancient continents, the continent of Laurania, which would eventually become North America, and the continent of Baltica, which would eventually become Scandinavia and the Baltic states, closing the ancient Iapetus Ocean between them in a slow collision that lasted tens of millions of years and produced a mountain range that was, at its peak, comparable in height to the modern Himalayas. Peaks perhaps 8 or 9 kilometers high. A continuous chain of mountains stretching from what is now Scandinavia through Scotland and Ireland and Newfoundland and the northern Appalachians of eastern North America, all of it one mountain range, all of it built by the same collision, all of it sharing the same rocks and the same geological history. That mountain range is gone now. What remains of it are stumps, ancient, deeply eroded, worn-down roots of mountains that once stood perhaps 5 times higher than they do today. The Highlands of Scotland are the basement of mountains whose peaks were removed by erosion over 400 million years. The Appalachian Mountains of the eastern United States, which feel substantial to anyone who has hiked them, which were once considered a significant barrier to westward expansion in early American history, are themselves the eroded remnants of a range that was once among the highest on Earth. 400 million years of patient, relentless, grain-by-grain destruction reduced some of the greatest mountains the world has ever seen to gentle, rounded hills. And the process is still going on. Right now, tonight, everywhere on Earth where rock is exposed to the surface. The destruction of mountains is not a single process. It is a collaboration, a slow, patient conspiracy between several different physical and chemical agents, each working at its own pace and in its own way, but all contributing to the same end. The relentless reduction of high places to low ones, the grinding of solid rock to sand and silt, and dissolved ions carried away by rivers to the sea. The most powerful agent of mountain destruction is water. Not water in any dramatic form, not floods or tsunamis or the catastrophic release of a glacial lake, but ordinary water. Rain, the same rain that falls on every mountain range on Earth, that soaks into cracks in the rock, that pools in hollows, that runs in thin sheets down every slope. This ordinary water is, on geological timescales, extraordinarily destructive. When water enters a crack in a rock and then freezes, it expands by approximately 9%. This expansion exerts a force of up to 20,000 atmospheres of pressure on the surrounding rock. No rock can withstand this indefinitely. The crack widens. The next cycle of freezing widens it further. The rock eventually splits along the crack, producing a smaller fragment. That fragment is carried downhill by gravity, by the next rainfall, by the next freeze-thaw cycle, and eventually reaches a river, where it begins the long journey to the sea. This process, frost wedging, is happening on every mountain range in every part of the world where temperatures cycle above and below freezing. In alpine environments, where temperature swings through the freezing point can happen on a daily basis during transitional seasons, a single exposed rock face can undergo hundreds of freeze-thaw cycles per year, each one imperceptibly small in its effect. Accumulated over millions of years, together they dismantle a mountain. Water also attacks rock chemically, not just physically. Rainwater is a weak carbonic acid, formed when carbon dioxide from the atmosphere dissolves in water droplets to produce carbonic acid, H2CO3. This mild acidity reacts with the minerals in many common rocks, particularly the feldspars and other silicate minerals that make up granite and related rocks, breaking their crystal structures and converting them to clay minerals, quartz sand, and dissolved ions that are carried away in solution. This chemical weathering is invisible to any ordinary observation, but operates continuously on every exposed rock surface, slowly converting solid rock to soluble components and washing them away. Limestone and other carbonate rocks are particularly vulnerable to chemical weathering. The carbonic acid in rainwater dissolves limestone directly, carving the extraordinary landscapes of karst terrain. The caves and sinkholes and towering rock pillars of places like the Gillen Mountains of China, the Dolomites of northern Italy, and the caves of the Yucatan Peninsula. These landscapes are the visible evidence of mountains being dissolved, literally dissolved in water, over millions of years. Of all the agents of erosion, none is more spectacular in its effects or more patient in its operation than ice. Not the thin sheets of ice that form on a frozen pond, or the icicles hanging from a winter eve, but glacial ice. The slowly moving rivers of compressed snow and ice that flow down mountain valleys and across continental plains at speeds ranging from a few centimeters to a few meters per day, carrying within their base and their margins everything they've scraped from the bedrock beneath them, grinding it, crushing it, polishing it, and eventually depositing it somewhere far from its origin. A glacier is not passive. It does not simply rest on the mountain and slowly melt. It moves, driven by its own weight, by the pressure of the ice accumulating in the snowfields at its upper end, by the slow internal deformation of the ice crystals under stress. A glacier flows downhill with a kind of ponderous, unstoppable determination. At its base, where the pressure is greatest, a thin film of meltwater allows the glacier to slide over the bedrock. And embedded in that base, like sandpaper on a sanding block, are fragments of rock plucked from the valley walls and floor, grinding the bedrock beneath with every meter of the glacier's advance. The results of this grinding are visible in every landscape that was glaciated during the ice ages of the past 2 million years. The distinctive U-shaped valleys of the Alps and the Scottish Highlands and the fjords of Norway, with their flat floors and steep sides, are the excavations left by glaciers that carved through what had been V-shaped river valleys, widening and deepening them over hundreds of thousands of years. The long, narrow lakes of the English Lake District, the Swiss Lakes, the Finger Lakes of New York State, all occupy basins carved by glacial erosion into the underlying rock. Yosemite Valley in California, one of the most celebrated landscapes in North America, is a glacially carved valley. Its sheer granite walls the product of the same slow grinding that has been dismantling mountains since the ice ages began. The rock that glaciers remove does not simply disappear. It is carried, embedded in the moving ice, sometimes for hundreds of kilometers, and deposited when the glacier retreats. The rolling hills of the American Midwest, the gentle landscapes of the northern European plain, the fertile agricultural land of the Canadian prairies are all built on glacial deposits, on the ground-up debris of mountains that no longer exist, spread across lowlands by the slow transport of glaciers and their meltwater rivers. Mountains are not just eroded, they are relocated, piece by piece, grain by grain, dissolved ion by dissolved ion. The material of a mountain is transported downhill and eventually carried by rivers to the sea, where it settles to the ocean floor and becomes the sedimentary rock of the future, the raw material from which future mountains, compressed and uplifted by future tectonic collisions, will eventually be built. Rock is recycled. Mountains are temporary arrangements of matter. The atoms in the granite beneath the Alps today were once part of a sea floor, compressed and heated and intruded as magma into the crust during an earlier mountain building event, then exposed by the erosion of that earlier mountain range, then deposited as sediment in another sea, then compressed and metamorphosed and intruded again by the magma associated with the alpine collision. Those atoms have been through multiple mountain ranges. They will go through more. To understand what 400 million years of erosion looks like, consider the Appalachian Mountains of eastern North America more carefully. They offer perhaps the best illustration on Earth of the full arc of a mountain range's life, from birth to advanced old age, because they are genuinely ancient, among the oldest exposed mountain roots on the planet, and because their history has been studied in extraordinary geological detail. The Appalachians were built not once, but multiple times, through a series of tectonic collisions spanning from roughly 500 million years ago to roughly 300 million years ago, the result of repeated closings and openings of ocean basins as the continents of the ancient world drifted together and apart in the long dance of the Paleozoic era. The final major event was the collision with Africa as Pangaea assembled, which produced the highest peaks the range ever achieved. At their maximum, perhaps 300 million years ago, the highest peaks of the Appalachians may have stood as high as 8 or 9 kilometers above sea level, as high as the modern Himalayas, as high as the highest point on the Earth's surface today. Imagine the Himalayas stretched along the eastern seaboard of North America, from Alabama to Newfoundland, a wall of rock and ice and snow as dramatic and as imposing as anything the modern world contains. 300 million years of erosion have reduced those peaks to what you see today. The highest point in the Appalachians is Mount Mitchell in North Carolina, at approximately 2,037 meters above sea level. 2 kilometers. The mountains that once stood 9 kilometers high are now 2 kilometers high. 7 kilometers of rock have been removed by erosion over 300 million years. 7 kilometers of granite and schist and gneiss, ground to sand and silt and dissolved minerals, carried by rivers to the ancient coastal plains and eventually to the sea. That 7 kilometers of eroded rock now lies, in part, beneath the coastal plain of the eastern United States, the broad, flat lowland between the Appalachians and the Atlantic coast. The material that once formed the peaks of the ancient mountains is now the substrate of the cities of the eastern seaboard, buried under sediment, compressed and lithified into new sedimentary rock, waiting for the next tectonic event that will compress it and heat it and eventually push it up into a new mountain range. The mountains give themselves to the lowlands. The lowlands, in time, become the mountains. The cycle continues, driven by the heat of the Earth's interior and the gravity of the Earth's surface, patient and perpetual and utterly indifferent to the brief presence of the organisms that live on the surface in between. If the Appalachians show us the old age of a mountain range, the Himalayas show us youth. Vigorous, dramatic, still rising, still building youth. The Himalayas are the product of the collision between the Indian plate and the Asian plate that began approximately 50 million years ago and continues today, and they're among the youngest major mountain ranges on Earth. At 50 million years old, the Himalayas are young by geological standards. Young enough that erosion has not yet had time to substantially reduce their height. Young enough that the building is still outpacing the destruction. Young enough that Mount Everest is still rising by approximately 4 millimeters per year. The rate of crustal thickening driven by the ongoing collision slightly exceeding the rate of glacial and fluvial erosion. But the erosion is working. The glaciers that descend from the high peaks of the Himalayas are among the most active and extensive in the world outside the polar regions. The rivers that drain the Himalayas, the Ganges, the Brahmaputra, the Indus, the Irrawaddy, carry an extraordinary load of sediment, the ground-up debris of the mountains, to the sea. The Ganges-Brahmaputra Delta, where those rivers empty into the Bay of Bengal, is one of the largest river deltas on Earth, built from the sediment eroded from the Himalayas over 50 million years. The material that was once the seabed of the Tethys Ocean, uplifted by the collision into the highest mountains on Earth, is being carried grain by grain back to the sea. In 50 million years, if the collision between India and Asia has slowed or stopped, and if no new tectonic event has reinvigorated the range, the Himalayas will be lower and more rounded. In 100 million years, they may look somewhat like the Appalachians do today. In 300 million years, they may be nothing but ancient roots, low hills of metamorphic rock exposed at the surface, the last faint remnants of a range that once contained the highest point on the planet. Every mountain range follows this arc birth in a tectonic collision. Growth as the building exceeds the erosion, a period of maximum height and drama. Then the long, slow decline as erosion takes over from building, as the colliding plates slow or separate, as the roots of the mountains sink into the mantle under their own weight, and the peaks above are slowly, grain by grain, carried away. Every mountain you have ever seen, every summit you have ever climbed or admired from a distance, is in the middle of this arc. Some are young and rising. Some are old and declining. None is permanent. All of them are in the process of being destroyed right now, tonight, as you rest, and as the rain falls and the rivers run and the glaciers grind. Here is a thought to carry with you as you drift towards sleep. The sand on a beach is not a simple thing. It is not merely broken rock in a convenient size. It is the end product of a process that may have taken hundreds of millions of years. Each grain of quartz sand on a beach has a history that, if you could read it, would tell you about the mountain it came from, the river that carried it, the ocean current that sorted it, the beach that received it. Many sand grains are remarkably old. Quartz, the mineral that makes up most beach sand, is chemically resistant and mechanically hard, and it survives the journey from mountain to beach with its crystal structure essentially intact. A grain of quartz sand on a beach in North Carolina may have been part of the Appalachians when they were still high mountains. It may have been carried by rivers to an ancient coast, deposited, lithified into sandstone, uplifted again into a later mountain range, eroded again, carried again, deposited again, in a cycle repeated multiple times over hundreds of millions of years. The sand is ancient. The sand is the mountain's last form before it returns to the sea, and the sea over millions of years, will deposit that sand as sediment on the ocean floor. The sediment will be compressed and lithified into new sedimentary rock. That rock will be carried by tectonic plates into a collision zone. It will be compressed and metamorphosed and pushed upward into a new mountain range. And the cycle will begin again. The mountain that is being destroyed tonight will eventually become a new mountain, in a different place, in a different configuration. After a journey of hundreds of millions of years through rivers and ocean floors and tectonic plates, nothing is lost. Everything is recycled. The Earth is a closed system of matter, endlessly rearranging itself under the influence of its internal heat and the gravity of its own mass. Patient beyond any human comprehension, creative beyond any human imagination. Let that thought be with you as you breathe. Somewhere on some mountain, a grain of rock is separating from its parent cliff face tonight. It will spend the next 100 million years traveling to the sea, and it will eventually become something entirely different from what it is now. Everything, in enough time, becomes something else. Even the mountains, even us. There is a creature living in the shallow tide pools of the rocky coastlines of the Pacific Ocean that looks, at first glance, like a small oval stone, pale gray or greenish, slightly domed, no more than 5 centimeters long, clinging to the rock with a muscular foot so powerful that removing it by force would sooner destroy the animal than detach it from its surface. It has 8 overlapping shell plates along its back. It has a mouth on its underside, surrounded by a rasping ribbon of teeth called a radula. It has no eyes, no brain in any sense we would recognize, no ability to move with any purpose across more than a few centimeters of rock in a lifetime. This creature is a chitin. In its basic body plan, that 8-plated oval, that rasping radula, that powerful adhesive foot, is essentially unchanged from chitin fossils found in rocks 500 million years old. 500 million years. While the continents drifted and collided and drifted again. While mountains rose and were ground to sand and rose again. While the atmosphere changed its composition. While the oceans changed their chemistry. While the climate swung from snowball Earth to greenhouse hothouse and back multiple times. While every other complex animal lineage on the planet transformed itself, branching into insects and fish and amphibians and reptiles and birds and mammals, the chitin remained essentially the chitin. The same shape, the same 8 plates, the same foot, the same radula. Evolution is the subject of this chapter. And the first thing I want to say about it, the thing that I think is most often missed in popular accounts of evolution that emphasize dramatic transformations and rapid change, is that evolution is extraordinarily, magnificently slow. Not always. Not in every case. There are examples of evolution operating on timescales visible within a human lifetime, in bacteria developing antibiotic resistance over years. In the Galapagos, finches whose beak shapes shifted measurably over decades in response to drought. Evolution can be fast, but evolution at the scale we will discuss tonight, the evolution of body plans, of new major groups of organisms, of the fundamental architecture of life, operates on timescales measured in millions and tens of millions and hundreds of millions of years. A million years between heartbeats. That is the scale at which the deepest changes in life's history occur. Charles Darwin, sitting in his study at Down House in Kent in the 1850s, working through the implications of what he had observed on his voyage on the Beagle and in his decades of subsequent research and correspondence, arrived at an idea so simple and so powerful that it took the better part of a century for its full implications to be absorbed into the body of science. The idea is this: organisms within a population vary. They differ from each other in ways that are, at least partly, heritable, passed from parents to offspring. Some of these variations make their bearers slightly better suited to survive and reproduce in their particular environment. Those individuals produce more offspring than those with less favorable variations. Their offspring inherit the favorable variations. Over generations, the frequency of the favorable variations increases in the population. Over enough generations, the accumulation of small, incremental changes can produce a population that is so different from the ancestral one that we would call it a different species. Natural selection, the differential survival and reproduction of heritable variations. That is the mechanism, and it operates so slowly, with changes so small from one generation to the next that no observer watching in real time would see anything happening at all that it was not discovered by watching organisms change. It was inferred retrospectively from the pattern of similarities and differences among living organisms and from the fossil record of ancient life. The raw material of evolution is mutation. Random changes in the sequence of DNA caused by copying errors during cell division, by damage from radiation or reactive chemicals, by the movement of genetic elements within the genome. Most mutations are neutral, having no significant effect on the organism that carries them. Some are harmful, reducing the organism's fitness. A small fraction are beneficial, improving survival or reproduction in some specific environmental context. These beneficial mutations are the ones that natural selection favors, gradually increasing their frequency in the population over generations. A generation in a bacterium is 20 minutes. A generation in a fruit fly is 2 weeks. A generation in an elephant is perhaps 20 years. The rate at which evolution proceeds depends partly on the generation time, partly on the size of the population, partly on the strength of the selective pressure. For large, slow-reproducing organisms in stable environments, evolution can be extraordinarily slow. For small, fast-reproducing organisms under strong selective pressure, it can be remarkably rapid. But even the fastest evolutionary changes in large organisms, the kind of changes that lead to new species, new body plans, new fundamental ways of being alive, take thousands to millions of years. And the deepest changes in the history of life, the appearance of the major animal body plans, the transition from sea to land, the development of flight, the evolution of complex brains and consciousness, took tens to hundreds of millions of years. These are the changes we explore tonight. Approximately 540 million years ago, in a geologically brief interval spanning perhaps 20 to 25 million years, the basic body plans of almost all the major animal groups alive today appeared in the fossil record for the first time. Arthropods with their jointed exoskeletons and compound eyes, mollusks with their shells and mantles, echinoderms with their radial symmetry, chordates, the group that would eventually produce fish and amphibians and reptiles and birds and mammals, and therefore us, with their characteristic nerve cord and gill slits, annelid worms, priapulid worms, brachiopods, a bewildering diversity of body plans, some of them familiar, some of them representing entirely extinct experiments in animal architecture, appearing within what is, by geological standards, a very short time. This event is called the Cambrian explosion, and it is one of the most studied and most debated events in the history of life. Was it truly explosive, a genuine rapid diversification? Or is it partly an artifact of the fossil record, an apparent sudden appearance that reflects the evolution of hard parts, shells and skeletons that fossilize well, in animals whose soft-bodied ancestors had long existed but left few traces? The answer is probably some of both. The acquisition of hard parts was itself an evolutionary innovation, that opened new ecological possibilities and drove genuine rapid diversification. But the soft-bodied ancestors of the Cambrian animals almost certainly existed before the explosion proper, and some of them may be represented in the mysterious Ediacaran fossils of the preceding period. What the Cambrian explosion tells us, whatever its exact interpretation, is that the evolution of the major animal body plans took place on a timescale of tens of millions of years. 20 million years sounds fast in this context, and it was fast by geological standards, faster than most major evolutionary transitions. But 20 million years is still an interval during which approximately 1 million human generations could have lived and died if humans had existed then, which they emphatically did not. 20 million years, a million generations, and at no point during that entire interval would any individual organism have noticed any change in its species. Each generation would have been essentially identical to the one before it. The change would have been invisible from the inside, perceptible only to a mind capable of looking backward across millions of years at the accumulated divergence between the first generation and the last. Of all the evolutionary transitions in the history of life on Earth, few are more dramatic or more consequential than the movement of animals from the sea onto dry land. It represents not merely a change of habitat, but a complete redesign of the physiological systems that sustain life, a transformation of every major organ system to cope with an environment radically different from the one in which life had spent the previous 3 billion years. Water supports the body. Air does not. An animal moving from water to land needs a skeleton capable of supporting its weight against gravity, a completely different challenge from the buoyancy-assisted existence of an aquatic animal. Water provides oxygen dissolved throughout the medium. Air provides oxygen only at the surface and only to animals with lungs or equivalent air-breathing structures capable of extracting it. Water prevents desiccation. Air dries the body's surfaces continuously, and an animal living in air must have skin or integument capable of resisting water loss, or must have behavioral strategies for finding and retaining moisture. The evolution of the first truly terrestrial vertebrates, the amphibians from their lobe-finned fish ancestors, took place over approximately 20 million years in the Devonian period, roughly 380 to 360 million years ago. The fossil record of this transition is now remarkably well documented, partly because of the discovery of a spectacular transitional fossil called Tiktaalik rosei, found in the Canadian Arctic in 2004 and formally described in 2006. Tiktaalik was a large, flattened fish, perhaps 2 to 3 meters long, that lived in shallow freshwater environments approximately 375 million years ago. It had gills and scales like a fish, but it also had a neck, the first vertebrate with a neck that could move independently of its body. It had ribs capable of supporting the weight of its organs against gravity. Its fins contain the bones that are homologous to the upper arm, forearm, and wrist bones of all subsequent terrestrial vertebrates, including your own arm. Those fin bones could support the animal's weight and be used to prop itself up or to push through shallow water and over obstacles. Tiktaalik is not the direct ancestor of amphibians, but it is a close relative of whatever was, and it gives us an extraordinarily clear picture of what the transition from fin to limb, from fish to amphibian, looked like in its intermediate stages. It shows us that the transition was not a sudden leap, but a gradual accumulation of features, each one a small modification of what came before, each one marginally better suited to the shallow, obstacle-filled, occasionally air-breathing environment in which these animals lived. From Tiktaalik to the first true tetrapod, the first four-limbed animal capable of walking on land, took perhaps 10 to 20 million years. 10 to 20 million years of generation after generation of slightly different fish and fish-like tetrapods, each one barely distinguishable from its parents, all of them living out their lives in shallow coastal swamps and river deltas, none of them aware that they were in the process of conquering a new world. And then, 360 million years ago, the first amphibians walked on land. Everything that has walked on land since, every frog and salamander and lizard and dinosaur and bird and mammal and human being, is descended from that moment. From those first awkward steps on a dry land, those first breaths of air through primitive lungs, those first eyes blinking in an environment that no vertebrate had ever inhabited before. It took 20 million years of unobservable, imperceptible, generation-by-generation change to produce that moment. If the transition from sea to land is evolution's greatest story of expansion into new territory, the evolution of the whales is perhaps its most dramatic story of return. And it is one of the best documented major evolutionary transitions in the fossil record, a sequence of fossils so complete and so carefully dated that we can follow the transformation from land-dwelling mammal to fully aquatic whale in extraordinary detail. Approximately 55 to 50 million years ago, in what is now Pakistan and India, a small four-legged, land-dwelling mammal called Pakicetus lived near the shores of the ancient Tethys Sea. Pakicetus looked somewhat like a large dog or a small wolf, with a long skull, strong legs, and a heavy tail. It was a carnivore, probably eating fish and other aquatic prey from the shoreline. Its ear bones, analyzed in detail by paleontologists, already showed the distinctive structure that characterizes all modern whales and dolphins, a specific arrangement that transmits sound through the lower jaw in a way that functions well for hearing underwater. Pakicetus is the earliest known ancestor of the whales, and from Pakicetus, over approximately 15 million years, the whale lineage transformed itself from that dog-sized shoreline predator into a fully aquatic animal. The fossil record documents this transformation in remarkable detail. Ambulocetus, living approximately 49 million years ago, was an amphibious animal, capable of both walking on land and swimming. Its hind legs still functional for terrestrial locomotion, but its body already elongated and its limbs modified for powerful swimming. Rhodocetus, at about 47 million years ago, was more fully aquatic, its hind legs reduced, and its tail apparently already developed into the horizontal flukes characteristic of modern whales. By 40 million years ago, the basilosaurids were enormous, fully aquatic, serpentine animals 30 meters long, with vestigial hind limbs no longer useful for locomotion, fully committed to the sea. 15 million years, from a dog-sized shoreline predator to a 30-meter, fully aquatic leviathan. In 15 million years of unobservable, continuous, incremental change, the entire architecture of a mammalian body was redesigned for life in the ocean. Legs became flippers. Nostrils migrated from the tip of the snout to the top of the skull to become the blowhole. The neck vertebrae fused to stiffen the body for swimming. The hind legs shrank and were absorbed into the body wall. The tail was modified into horizontal flukes. Every one of those changes happened one small mutation at a time, selected over thousands of generations, invisible in any individual lifetime, visible only in the accumulated record of millions of years. You are the product of evolution, not in some distant, abstract, ancestral sense, but directly and personally. The specific sequence of DNA in every cell of your body is the result of an unbroken chain of evolutionary change stretching back 4 billion years to the first self-replicating molecules in the primordial ocean. Every organism in that chain survived long enough to reproduce. Every one of them passed on a slightly modified version of the genetic information that, through billions of rounds of copying and selection and modification, eventually produced you. Your most recent common ancestor with a chimpanzee, your closest living relative, lived approximately 6 to 7 million years ago. A single species of ape, somewhere in Africa, was the ancestor of both the modern chimpanzee lineage and the modern human lineage. 6 to 7 million years of separate evolution, roughly 300,000 generations of hominins on one side and 300,000 generations of chimpanzees on the other, produced the differences between you and the chimpanzee. The differences that feel so vast and so fundamental: the upright posture, the large brain, the language, the hands capable of writing and playing instruments and performing surgery, all of it accumulated in 300,000 generations. 300,000 generations is a large number by human intuition, but is actually quite small by evolutionary standards. 300,000 generations is why chimpanzees and humans share approximately 98.7% of their DNA. The differences are real and profound in their effects, but they are, in the genetic record, a thin layer of change painted over an enormous shared foundation. Your most recent common ancestor with a fish lived approximately 450 million years ago. With an insect, perhaps 600 million years ago. With a mushroom, perhaps 1 billion years ago. With a bacterium, perhaps 3.5 billion years ago. All of these organisms are your relatives. Not metaphorically, genetically. The DNA evidence places them on the same tree of life, connected to you by an unbroken chain of ancestry stretching back to the origin of life on Earth. You carry, in the sequence of your genome, the echoes of 4 billion years of evolution. Genes that you share with yeast and with fish and with plants and with bacteria. Genes so ancient and so fundamental that evolution has preserved them essentially unchanged across billions of years because any mutation in them is lethal. The histone proteins that package your DNA into chromosomes are almost identical to the histone proteins in a yeast cell. The machinery that replicates your DNA is essentially the same machinery that replicates the DNA of every living thing on Earth. You are 4 billion years old in the parts that matter most. The parts that make you specifically human, the large brain, the upright posture, the language capacity, those are the recent additions, the thin layer of novelty painted over an ancient foundation. And the process that produced all of it is still running. Your children, if you have them or will have them, will carry mutations that you do not carry. Some of those mutations will be neutral. A very small number will be slightly beneficial. Over thousands of generations, the beneficial ones will spread through the population. Over millions of generations, the accumulated changes will make the humans of that distant future different from you in ways that are, right now, entirely unpredictable. Evolution has not stopped. It has not reached an endpoint in us. We are not the final form of anything. We are a stage in a process that has been running for 4 billion years and that, barring extinction, will continue running for billions more. And none of it will be visible to any individual alive at any given moment. It is all happening too slowly to see. One generation at a time, one mutation at a time, one small, imperceptible, patient step at a time. Just like the mountains eroding, just like the continents drifting, just like everything else that matters most in the deep history of this world. Beneath your feet, right now, there's a fire that has been burning for 4.5 billion years. Not a fire in the ordinary sense. Not combustion. Not the rapid oxidation of fuel that produces the flame of a candle or the blaze of a forest fire. Something older and stranger and far more patient. The heat of the Earth's interior is the residual warmth of the planet's violent birth, supplemented by the slow decay of radioactive elements. And it has been leaking outward through the rock of the mantle and crust since the Earth first coalesced from the spinning disk of gas and dust that surrounded the young sun 4.5 billion years ago. At the center of the Earth, approximately 6,371 kilometers below the surface where you're lying, the temperature is approximately 5,000 to 6,000 degrees Celsius, roughly the same temperature as the surface of the sun. The pressure is approximately 360 gigapascals, 3.5 million times the pressure of the atmosphere of the Earth's surface. Under these conditions, iron and nickel, the primary components of the Earth's core, exist in a state unlike anything we encounter at the surface. The inner core is solid despite those temperatures, because the pressure is so extreme that the melting point of iron is pushed above the actual temperature. The outer core is liquid, a vast churning ocean of molten iron and nickel thousands of kilometers deep, whose slow convective motion generates the Earth's magnetic field. This fire at the center of the world is going out. Slowly, imperceptibly, but inexorably, the Earth is cooling. It has been cooling since the moment it formed. And when it has finally cooled completely, when the last of its internal heat has leaked away into space, the Earth will become a geologically dead planet. No more plate tectonics. No more volcanism. No more magnetic field. A cold, still, geologically frozen world. That moment is very far in the future. But the cooling is happening now, tonight. One infinitesimal degree at a time. To understand why the Earth is still so hot 4.5 billion years after its formation, we need to understand how hot it was at the beginning and why it got that hot in the first place. The Earth did not form gently. It formed in a process of extraordinary violence, the accretion of rocky planetesimals, bodies ranging in size from pebbles to small planets, that orbited the young sun in a dense, chaotic disk and collided with each other constantly, merging and growing into larger and larger bodies over millions of years. Every collision released energy. The kinetic energy of impacting bodies was converted on impact into heat. As the proto-Earth grew larger, the impacts grew more energetic and the rate of heating accelerated. By the time the proto-Earth had accumulated most of its mass, the energy of accretion had melted much or all of it. The early Earth was a magma ocean, a globe of molten or partially molten rock and metal, with a surface temperature of perhaps several thousand degrees and an interior even hotter. In this magma ocean, the denser components sank toward the center and the lighter ones rose toward the surface, a process called differentiation. The iron and nickel that make up the core sank inward. The silicate rocks that make up the mantle and crust rose outward. The Earth sorted itself by density into its layered structure. Then, approximately 4.5 billion years ago, very early in the Earth's history, a body approximately the size of Mars, a fully formed planet that had been orbiting the Sun in a nearby orbit, struck the proto-Earth in a glancing collision of incomprehensible violence. The impactor, which scientists have named Theia, was largely absorbed into the Earth, contributing its iron core to the Earth's core and its mantle material to the Earth's mantle. But the enormous energy of the impact vaporized a large fraction of the Earth's outer layers and blasted them into orbit, where they reaccreted to form the Moon. The giant impact reset the Earth's heat. The energy of a planet-scale collision was added to the already enormous heat of accretion, melting the Earth's surface again and producing a second magma ocean phase. The Earth, after the giant impact, was a ball of molten rock glowing orange-red in space, slowly radiating its heat into the void. From that incandescent beginning, the Earth has been cooling ever since. 4.5 billion years of cooling, and the core is still at 5 to 6,000 degrees. The rock is an extraordinarily poor conductor of heat. Heat moves through solid rock by conduction at a rate so slow that the temperature gradient from the core to the surface, spanning 6,000 kilometers, has barely changed in billions of years. Accretional heat alone, the heat stored since formation, is not sufficient to explain why the Earth's interior is still so hot 4.5 billion years later. Pure conduction of the original heat would have cooled the Earth substantially more than we observe. There must be an additional heat source, one that has been replenishing the Earth's internal heat throughout its history. That source is radioactivity. Specifically, the decay of 4 long-lived radioactive isotopes: uranium-238, uranium-235, thorium-232, and potassium-40. These isotopes, incorporated into the Earth's rock when the planet formed from the solar nebula, decay at precisely known rates, releasing heat as their atomic nuclei transform into more stable configurations. They are distributed throughout the mantle and crust, a diffuse, invisible heat source that has been supplementing the primordial accretional heat for 4.5 billion years. The half-lives of these isotopes are conveniently comparable to the age of the solar system. Uranium-238 has a half-life of approximately 4.5 billion years, almost exactly the age of the Earth. This means that the Earth today contains approximately half the uranium-238 it had when it formed. Uranium-235 has a half-life of about 700 million years, meaning the Earth has lost roughly 98% of its original uranium-235. Thorium-232 has a half-life of about 14 billion years, so the Earth has lost relatively little of its thorium. Potassium-40 has a half-life of about 1.2 billion years. In the early Earth, when concentrations of these isotopes were higher because less of them had yet decayed, the radioactive heat production was substantially greater than it is today. Estimates suggest that the total heat production from radioactive decay in the early Earth was perhaps 3 to 4 times higher than it is now. This higher heat production in the early Earth drove more vigorous mantle convection, faster plate tectonics, and more active volcanism than we observe today. The young Earth was a more geologically energetic planet than the middle-aged one we inhabit. As the radioactive isotopes continue to decay and their concentrations decrease, the radioactive heat input will diminish. The Earth's internal heat engine will gradually slow. The mantle convection will become less vigorous. Plate tectonics will slow and eventually, in the very distant future, stop entirely. But that is billions of years away. For now, the radioactive decay continues its patient, invisible exothermic work in the rocks beneath your feet, keeping the mantle warm enough to convect, keeping the plates moving, keeping the Earth geologically alive. The Earth's magnetic field is one of the most important consequences of the planet's still hot, still churning interior, and one of the most direct illustrations of why the slow cooling of the core matters for everything that lives on the surface. The liquid outer core, that vast ocean of molten iron and nickel convecting under the combined influence of the Earth's internal heat and the Coriolis effect of the planet's rotation, is the source of the Earth's magnetic field. The convective motion of electrically conducting liquid iron, combined with the Earth's rotation, generates electric currents within the outer core, and those electric currents generate the magnetic field that extend from the core through the mantle and crust and out into space, forming the magnetosphere that surrounds the planet. The magnetosphere is the Earth's shield. It deflects the solar wind, the constant stream of charged particles emitted by the sun, preventing those particles from stripping away the Earth's atmosphere. Without the magnetic field, the solar wind would gradually erode the atmosphere over geological time, as appears to have happened to Mars, which lost its global magnetic field approximately 4 billion years ago and subsequently lost most of its atmosphere and liquid water. The magnetic field is, in a very direct sense, one of the reasons the Earth is habitable. One of the reasons there's an atmosphere to breathe and an ocean to sustain life. And the magnetic field is a product of the core's heat. As long as the outer core remains liquid and convecting, the geodynamo will operate and the magnetic field will be sustained. When the core eventually cools enough for the outer core to solidify, the geodynamo will cease, the magnetic field will decay, and the Earth will be exposed to the full force of the solar wind. That moment is billions of years in the future. The core has enough heat to sustain the geodynamo for at least another billion years, probably longer. But it is coming, slowly, at the pace of geological cooling. 1 degree at a time, 1 billion years at a time, the fire at the center of the world is going out. And with it, eventually, will go the shield that protects the surface. If you want to see what the Earth will eventually become, after its internal heat is exhausted and its geological engine has shut down, you do not need to look far. You need only look at the 4th planet from the Sun. Mars is a small planet. Its mass is approximately 1/10 the mass of the Earth. Smaller planets have a higher surface area to volume ratio, which means they lose their internal heat more quickly relative to the amount they have. Mars cooled faster than Earth. Its core solidified earlier. Its mantle convection slowed and stopped. Its plate tectonics, if it ever had anything resembling plate tectonics in its early history, ceased billions of years ago. The evidence of Mars's geological death is written clearly across its surface. The volcanoes of Mars, including Olympus Mons, the largest volcano in the solar system, standing 22 kilometers high and spanning 600 kilometers at its base, are not distributed across a network of moving plates the way Earth's volcanoes are. They are stationary hotspots, places where a plume of warm mantle material rose through the lithosphere and erupted at the surface. And because the Martian lithosphere did not move over the plume, the eruptions piled up in the same location for billions of years, building the enormous edifices we see today. The last significant volcanic activity on Mars may have been only a few 100 million years ago, recent by geological standards, but the planet is largely dormant now. The surface of Mars is ancient and unchanging in a way that the Earth's surface is not. Without plate tectonics to recycle the crust, to subduct old rock and generate new rock at spreading centers, the Martian surface preserves features billions of years old. The southern highlands of Mars, the ancient, heavily cratered terrain that covers much of the planet's southern hemisphere, date to the first billion years of the solar system, a period so ancient that essentially nothing of equivalent age survives on the Earth's surface, where plate tectonics has continuously recycled the crust. Mars also lost its magnetic field. The evidence for this is in the ancient magnetized rocks of the Martian crust, which record the existence of a global magnetic field in the planet's early history that subsequently ceased when the core cooled and solidified. Without a magnetic field, the solar wind stripped away the Martian atmosphere over billions of years, leaving the thin, cold, carbon dioxide-rich atmosphere that exists today, with a surface pressure less than 1% of Earth's. The liquid water that once flowed across the Martian surface, carving the ancient river valleys and lake basins that we can see in orbital images, evaporated or froze as the atmosphere thinned and has been locked in the polar ice caps and the permafrost ever since. Mars is the Earth's future in the very long run. Not in a billion years, not in 5 billion years, perhaps not for much longer than that, given the Earth's much larger mass and its correspondingly larger reservoir of internal heat. But eventually, the Earth will cool as Mars has cooled. The plates will stop moving. The volcanoes will go quiet. The magnetic field will fade. The atmosphere will thin. And the Earth will become a cold, silent, geologically frozen world, preserving in its ancient rocks the record of 4 billion years of extraordinary geological and biological activity that will, by then, be long over. That future is so far away that it is difficult to relate to personally. But the process is underway. The Earth is cooling now, tonight, one infinitesimal fraction of a degree at a time, one radioactive decay at a time, one convective overturn of the mantle at a time. The fire at the center of the world is going out. Slowly, patiently, on the only time scale that fire of that magnitude knows. The rate at which the Earth loses heat to space can be measured. Geophysicists have placed heat flow meters in boreholes drilled into the ocean floor and into the continental crust all over the world, measuring the rate at which heat conducts upward through the rock from the interior. These measurements, combined with geophysical models of the Earth's interior, give us a reasonably precise picture of the Earth's current rate of heat loss. The Earth loses approximately 47 terawatts of heat to space. 47 terawatts. For comparison, the total energy consumption of human civilization is approximately 20 terawatts. The Earth is losing heat to space at roughly twice the rate that all of human industry, all of our cities and vehicles and factories and data centers combined, consume energy. And yet, at 47 terawatts, the cooling is still extraordinarily slow on a geological timescale. The Earth contains an enormous reservoir of heat, and losing 47 terawatts from that reservoir changes it by an imperceptible fraction each year. The core temperature is dropping by perhaps a fraction of a degree per million years. The mantle is cooling at a similarly glacial pace. Most of the Earth's heat loss occurs at the mid-ocean ridges, where hot mantle rock rises close to the surface and a thin oceanic crust allows heat to conduct outward relatively efficiently. The rest occurs through the continental crust, more slowly, through the thick insulating blanket of silicate rock that covers the continents. And some heat escapes directly through volcanic activity, through the eruption of magma that carries heat from the mantle directly to the surface. Every volcanic eruption is, in a small way, the Earth exhaling some of its primordial warmth. Every hot spring and geothermal vent is the Earth sweating slightly. Every earthquake that releases the stress built up by moving tectonic plates is the Earth's interior heat expressing itself in the only languages it knows. Movement, heat, transformation. The Earth is breathing. Slowly, its breath measured in millions of years. Its exhalations, volcanic eruptions, and mid-ocean ridge spreading, and the patient loss of heat through kilometers of rock. And you, lying on the surface of this quietly breathing planet, are supported by the warmth of a fire lit 4.5 billion years ago. A fire that warmed the first oceans in which the first life arose. A fire that drives the plates whose motion built every mountain range and opened every ocean and shaped every continent on which every organism that has ever lived made its home. A fire that generates the magnetic field that protects the atmosphere that you're breathing right now. You're alive because the Earth is still warm, and the warmth is still there tonight, flowing upward through the rock beneath you at 47 terawatts, patient and ancient and slowly, slowly fading. The standard model of particle physics, the theoretical framework that describes all known fundamental particles and their interactions, predicts that the proton is stable. In the standard model, a quantity called baryon number is conserved. Protons and neutrons are baryons, And the total number of baryons in the universe does not change in any standard model interaction. A proton cannot simply transform itself into lighter, non-baryonic particles without violating baryon number conservation, and the standard model forbids this. But the standard model is not the final word on physics. It is an extraordinarily successful and precisely tested theory, but it has known limitations and is almost certainly incomplete. It does not include gravity. It does not explain dark matter or dark energy. It does not explain why there is more matter than antimatter in the universe. And many theoretical extensions of the standard model, the so-called grand unified theories that attempt to unify the strong, weak, and electromagnetic forces into a single framework, predict that baryon number is not exactly conserved. In grand unified theories, the three non-gravitational forces of nature are different manifestations of a single underlying force that was unified at the extraordinarily high energies of the early universe. At the energies accessible in our current cold universe, the three forces appear distinct. But at the energy scales of the grand unification, roughly 10 to the 15th times the energy of a proton at rest, they merge. And at those energy scales, new particles exist that can mediate interactions that violate baryon number, that can, in other words, allow a proton to transform into lighter particles. These particles, the X and Y bosons of grand unified theories, are so massive, so energetic, that they cannot be created in any particle accelerator we could plausibly build. Their mass corresponds to an energy scale far beyond the reach of any foreseeable technology. But their virtual presence, their quantum mechanical influence, even when not directly created, can still mediate proton decay at an extraordinarily low rate, a rate that depends on the fourth power of the ratio between the proton mass and the grand unification scale. That ratio is very small, and because the decay rate goes as the fourth power of a very small number, the predicted proton lifetime in grand unified theories is extraordinarily long. The simplest grand unified theory, the SU-5 model developed by Howard Georgi and Sheldon Glashow in 1974, predicted a proton lifetime of approximately 10 to the 30th years. Subsequent, more sophisticated theories have pushed the predicted lifetime higher, to 10 to the 34th years or beyond, depending on the specific theoretical framework. 10 to the 34th years. This number is so large that it requires a moment of genuine attention to even begin to appreciate. The current age of the universe is approximately 10 to the 10th years. The proton's predicted lifetime, in the more modest grand unified theory estimates, is 10 to the 24th times longer than the current age of the universe. If you represented the age of the universe as a single grain of sand, the proton's lifetime would be a sphere of sand roughly 100 million kilometers in diameter, larger than the distance from the Earth to the Sun. And yet, because you contain 7 times 10 to the 27th protons, and because the decay rate applies to each proton independently, a proton lifetime of 10 to the 34th years would imply that, on average, approximately 1 proton in your body would decay every million years or so. Not in your lifetime, not in the lifetime of the human species, not in the lifetime of the solar system, but eventually. If protons decay, the decay should be detectable, at least in principle, not by watching a single proton, which would require waiting inconceivably long times, but by watching an enormous number of protons simultaneously. If you have enough protons, the statistics work in your favor. Even a very rare decay rate, occurring once every 10 to the 34th years per proton, will produce a measurable number of decays per year if you are watching enough protons at once. And so physicists built tanks. Enormous tanks of the purest water ever produced, containing billions of trillions of protons, surrounded by highly sensitive light detectors capable of registering the faint flashes of light that would be produced if a proton inside the tank were to decay. These tanks were built deep underground, beneath mountains or in mines, shielded by kilometers of rock from the cosmic ray particles that would otherwise produce false signals and overwhelm any genuine proton decay events. The first and most famous of these experiments was the Kamiokande detector in Japan, built in a zinc mine in the Japanese Alps in the 1980s and subsequently upgraded to the much larger Super Kamiokande detector, which contains 50,000 tons of ultra-pure water viewed by approximately 11,000 photomultiplier tubes. Super Kamiokande is one of the most remarkable scientific instruments ever built. A cylindrical tank 50 meters tall and 39 meters in diameter, filled with water so pure that it is transparent for distances of over 60 meters, so pure that it would leach minerals from your body if you drank it, in a cavern a kilometer underground. Wrapped in a lattice of glass, eyes watching for the faintest possible flash of light. Similar experiments have been built in other countries. The IMB detector in a salt mine in Ohio, the Sudin detector in Minnesota, the SNO detector in a nickel mine in Ontario, and others. Each one a cathedral of particle physics, built in the dark to watch for something that may never happen on any humanly relevant timescale. These experiments have been watching for decades, and they have not seen a single proton decay. Not one. The absence of observed proton decay is itself one of the most important results in modern particle physics. It places strict lower limits on the proton lifetime. Super Kamiokande has established that the proton lifetime, for the most commonly predicted decay mode, proton decaying to a positron in a neutral pion, is greater than approximately 10 to the 34 years. This result rules out the simplest grand unified theory, the original SU-5 model, which predicted a lifetime shorter than this. The more sophisticated theories that predict longer lifetimes are not yet ruled out. The experiment continues. Every day, the 50,000 tons of ultra-pure water in Super Kamiokande sit in their underground cavern, watched by their 11,000 glass eyes, waiting. Every day that passes without a signal extends the lower limit on the proton lifetime by another day divided by the number of protons in the detector. Every year of null result tightens the constraint. Every decade pushes the allowed theories into a smaller and smaller corner of theoretical space. Perhaps the proton is truly eternal, and no grand unified theory that predicts its decay is correct. Perhaps the proton lifetime is longer than any experiment we could plausibly build will ever be able to test. Perhaps the answer lies beyond the reach of experiment, in the permanent twilight zone between physics and philosophy. Or perhaps, someday, in some tank of ultra-pure water deep underground, one of the 11,000 photomultiplier tubes will register a flash. A tiny, precisely characterized flash, consistent with the predicted signature of a proton decay event. And the experiment that has been waiting for decades, watching a number of protons almost beyond comprehension, will finally see what it has been looking for. That moment would be one of the most significant in the history of physics. It would be direct evidence that matter itself is not eternal, that even the most stable particles of the ordinary world are, on the deepest timescales, transient. There is something philosophically vertiginous about the concept of proton decay that I want to sit with for a moment before we move on. Something that goes beyond the physics and touches something deeper about the nature of existence and permanence. We tend to assume in our ordinary lives that matter persists, that the atoms of the world are the permanent substrate of change, the fixed foundation on which events unfold. Things happen to matter. Things are made of matter. But matter itself, we tend to assume simply is. It does not happen. It does not process. It endures. The possibility of proton decay challenges this assumption at its root. If protons decay, then matter is not the permanent substrate of the universe. Matter is itself a process, a very slow process, slower than any other we will discuss tonight, but a process nonetheless. The atoms of the world are not eternal fixtures. They are temporary arrangements of more fundamental fields, stable on the timescales of stars and galaxies, but not on the deepest timescales of the universe's future history. If protons decay, then on a timescale of roughly 10 to the 40 years, depending on the specific decay mode and lifetime, all ordinary matter will have dissolved. Every proton in every atom, in every star and planet and grain of dust will have decayed into lighter particles. The universe will contain no atoms, no chemistry, no solid objects of any kind. Only electrons and positrons and photons and neutrinos, diffusing through an ever-expanding, ever-cooling void. Matter, the stuff of which everything we have ever seen or touched or been is made, is a phase of the universe that began with the Big Bang, when the matter-antimatter asymmetry left a residue of protons and neutrons, and that will end if protons decay, when the last proton dissolves into radiation in the unimaginably distant future. We're made of a phase. We are temporary structures within a temporary substrate, existing in a window of cosmic time between the Big Bang and the ultimate dissolution of matter. That window is, by any ordinary measure, enormous. It is billions of times longer than the current age of the universe. It is long enough to contain the entire future history of the stars, the entire future of whatever intelligent life may arise and evolve and think its thoughts and wonder its wonders across the cosmos. But is finite. If protons decay, everything made of protons is finite. And tonight, in the protons of the atoms of your body, that process may be underway. Invisibly, imperceptibly, at a rate so slow that you will lose no measurable fraction of your protons in 1 trillion times the age of the universe. But the process, if it exists at all, is running. Right now, in the dark, in you. Let me be honest with you about the uncertainty in this chapter in a way that I think is important and that the subject demands. We do not know that protons decay. We have never observed it. The theoretical arguments for proton decay are compelling, coming from some of the most sophisticated and carefully developed frameworks in all of physics. But theoretical elegance is not the same as experimental confirmation. The history of physics contains examples of beautiful theories that were wrong and of surprising experimental results that no theory predicted. Grand unified theories are theoretical constructs, not established facts. The proton's decay, if it occurs at all, may occur by mechanisms different from those currently predicted, or may not occur at all. What we do know with confidence is the lower limit. The proton's lifetime, if it is finite, is greater than 10 to the 34th years for the dominant decay mode. That is an experimental fact established by careful observation over decades. Everything else, the theoretical predictions, the specific decay modes, the precise lifetime, remains uncertain. This uncertainty is not a failure of science. It is the frontier of science. It is the place where the known gives way to the unknown, where the well-tested theory gives way to the speculative, where the experiment has pushed as far as it currently can and has not yet found what it was looking for. The frontier is where science is most alive, most interesting, most genuinely engaged with questions that do not yet have answers. Whether the proton decays or endures forever, the question itself is worth asking. The experiment is worth running. The 50,000 tons of ultra-pure water in the dark cavern under the Japanese Alps is worth watching. Because if the answer is yes, if the proton does decay, the implications for our understanding of a universe's deepest structure and its ultimate fate are profound. And because the act of asking the question, of building instruments to listen for the whisper of matter dissolving in the dark, is itself one of the most extraordinary things that the matter of the universe has ever done. A collection of atoms, assembled by evolution into a creature capable of wondering whether atoms are eternal, building underground tanks of water to find out. The universe inspecting itself for cracks. That is us. That is what we do in the dark. On a clear night, far from city lights, the Milky Way is visible as a broad, luminous band arching across the sky from horizon to horizon. A river of light, soft and slightly mottled, made of the combined glow of hundreds of billions of stars too faint and too distant to be resolved individually by the naked eye, blending into a continuous pale shimmer that our ancestors watched for 10,000 years of recorded history and interpreted as rivers and roads and the spilled milk of gods. It looks fixed. It looks eternal. It looks like the most permanent thing the night sky has to offer, more permanent even than the individual stars it contains, which we know from mythology and astronomy alike can be born and can die. The Milky Way itself, the great river of light, seems simply to be there. A background, a constant, a feature of the sky as permanent as the sky itself. It is not permanent. It is not fixed. It is not still. Every star you can see in that luminous band is moving at speeds of tens or hundreds of kilometers per second relative to the galactic center, orbiting the center of the Milky Way in trajectories that take hundreds of millions of years to complete, drifting through the plane of the galaxy, oscillating gently above and below it, being tugged by the gravity of neighboring stars and giant molecular clouds and the spiral arms through which they pass. Slowly, over tens of millions of years, migrating from one part of the galaxy to another in a process called stellar migration or radial migration, drifting inward or outward from their birth orbits in response to the gravitational perturbations of the galaxy's large-scale structure. The galaxy is dancing, a dance so slow that a human civilization would have to last 100 million years to watch a single step. But the dance is happening. Right now, tonight, the stars are moving. The sun is orbiting the center of the Milky Way. This is a fact of astronomy so well established that it barely requires stating. And yet it is one of those facts that can pass through the mind without quite landing, without producing the genuine sense of motion and vertigo that it deserves. The sun is moving, not drifting aimlessly, not oscillating randomly, but traveling in a roughly circular orbit around the galactic center at a distance of approximately 26,000 light-years from the center, at a speed of approximately 230 kilometers per second. 230 kilometers per second. This is approximately 1,000th of the speed of light, and it is fast by any ordinary measure. A rocket traveling at 230 kilometers per second would cross the entire diameter of the Earth in less than 1/10 of a second. It would reach the moon in less than 2 seconds. And yet, at this speed, the sun takes approximately 225 to 250 million years to complete a single orbit around the galactic center. One galactic year, one cosmic year. The sun has completed approximately 18 to 20 of these orbits since it formed 4.5 billion years ago. And in each orbit, the sun traces a path approximately 160,000 light-years long. Everything in the solar system is making this journey with the sun, the Earth, the moon, every planet, every asteroid, every comet in the Oort cloud. You, all of it moving together through the galaxy at 230 kilometers per second, orbiting a center we cannot directly see because it is hidden behind thousands of light years of interstellar dust, completing one vast circuit every 250 million years. The last time the Sun was at its current position in its galactic orbit, the Permian-Triassic extinction, the greatest mass extinction in the history of complex life, was just beginning. Dinosaurs had not yet evolved. Mammals had not yet evolved. The continents were assembled into Pangaea. The Atlantic Ocean did not exist. In another 250 million years, when the Sun returns to this same position, the Earth, if it still exists and still has life, will be inhabited by organisms as different from us as we are from the early reptiles of the Permian. The continents will have rearranged themselves. The Himalayas may be worn to gentle hills. New mountain ranges may have risen elsewhere. The Atlantic may be closing. Everything we know will be gone, replaced by a world we cannot imagine, orbiting a sun that has aged by another 250 million years. And the Sun will simply have completed another lap. The Sun's orbit around the galactic center is not perfectly flat. The disk of the Milky Way has a gravitational pull that tends to pull stars toward its midplane, the thin, dense layer where most of the disk's mass is concentrated. But stars do not remain exactly in this midplane. Like a ball bouncing on a trampoline, they oscillate above and below it, drawn back toward the center by gravity each time they drift too far away, overshooting, rising above the plane, being pulled back, falling through, rising below, being pulled back again in a gentle vertical oscillation superimposed on the primary circular orbit. The Sun's vertical oscillation takes approximately 60 to 70 million years to complete a full cycle. Currently, the Sun is slightly above the midplane of the galactic disk and moving upward, away from the plane, at a speed of approximately 7 kilometers per second relative to the local standard of rest. In roughly 30 million years, it will reach its maximum height above the plane, perhaps somewhere between 50 and 100 light years above the midplane, and will begin falling back. It will pass through the midplane again in another 30 million years, continue downward, reach a maximum below the plane, and return. This gentle vertical bobbing may have consequences for the Earth and for life on its surface. The midplane of the galactic disk is the region of highest density of giant molecular clouds, the vast cold gas cloud from which new stars form, and of the disk's dark matter distribution. Each time the solar system passes through the midplane, it is exposed to a slightly denser environment of interstellar material, potentially increasing the flux of comets perturbed into the inner solar system, potentially slightly increasing the cosmic ray flux reaching Earth. Some researchers have proposed a connection between the Sun's oscillation through the galactic plane and the timing of major mass extinctions on Earth, suggesting that the increased comet flux or cosmic ray flux during midplane crossings could trigger extinction events. The evidence for this connection is contested and the statistical signal is not strong, but the idea is not absurd. The galaxy structure may have left its mark on the history of life on Earth through the subtle environmental changes associated with the solar system's slow galactic journey. Whether or not this connection is real, the oscillation itself is real. The Sun is bobbing, right now, 7 kilometers per second upward, away from the galactic midplane, on a journey that will take 30 million years to reach its apex. You will not notice the motion. Nothing you can perceive or measure with any instrument in your possession is sensitive to a 7 kilometer per second drift in the direction perpendicular to the galactic plane. What is happening? The galaxy is breathing, and we are riding one of its exhalations. The Sun's orbit is not perfectly circular and perfectly stable over billions of years. Stars do not simply follow fixed orbits around the galactic center the way planets follow fixed orbits around the sun, because the galaxy is not a simple, smooth gravitational potential like the sun's. The galaxy contains spiral arms, a central bar, giant molecular clouds, satellite galaxies, and other gravitational perturbations that can alter a star's orbit over time. Through a process called radial migration or churning, stars can drift significantly inward or outward from their birth radii over billions of years. The mechanism works through gravitational resonances with the galaxy's spiral arms. When a star's orbital period is in a particular ratio with the rotation rate of the spiral pattern, the two can exchange angular momentum efficiently. The star can gain angular momentum, moving it to a larger outer orbit, or lose angular momentum, moving it to a smaller inner orbit, depending on the details of the interaction. Over billions of years of repeated resonant interactions with the spiral arms, a star's orbit can shift by thousands of light years from its birth location. The sun itself may be a migrant. Stellar population studies and chemical abundance analyses suggest that the sun's chemical composition is slightly different from what would be expected for a star born at its current galactic radius. The sun is somewhat more metal-rich than typical stars at its current distance from the galactic center. This could indicate that the sun formed somewhat closer to the center of the galaxy, in a more chemically enriched inner disk, and has since migrated outward to its current position through radial migration. If this is correct, the sun is not native to its current galactic neighborhood. It is a traveler from the inner galaxy, a star that was born somewhere else and has been slowly drifting outward for billions of years. This has potentially important implications for the history of the Earth and of life. The inner galaxy is a more dangerous environment than the outer disk, with higher rates of supernovae, higher cosmic ray fluxes, higher densities of other stars that could perturb the outer solar system. If the sun formed in the inner galaxy and migrated outward, the Earth may have spent its early history in a more energetically active environment than it occupies today, and the migration outward may have contributed to the conditions that allowed complex life to develop. Or this may simply be a story we are telling ourselves, reading too much into the imprecise chemical abundances of a middle-aged star. The evidence for solar migration is suggestive but not definitive. The sun may have been born close to its current position and simply be chemically unusual for its location. But the phenomenon of stellar migration is real, even if the sun's specific history is uncertain. Stars do wander. The galaxy is not a collection of fixed orbits. It is a dynamic, evolving system in which the positions and velocities of its stars are constantly changing under the influence of the galaxy's own gravitational field and the perturbations of its structure. On timescales of billions of years, the galaxy mixes itself. Stars born in the inner disk end up in the outer disk. Stars born in the outer disk drift inward. The chemical enrichment produced by generations of dying stars is spread through the disk by this slow mixing, homogenizing the galaxy's composition over cosmic time. The stars that appear fixed in the night sky are not fixed. They have what astronomers call proper motion, a slow drift across the sky as each star follows its own path through the galaxy. The proper motion of most stars is tiny, measured in fractions of an arcsecond per year, far too small to detect without precise instruments over human timescales. The stars appear fixed to casual observation and have appeared fixed to every generation of human beings who has ever looked up at the night sky. But over tens of thousands of years, the proper motions of the nearby stars add up to produce measurable changes in the shapes of the constellations. The Big Dipper, for example, that familiar and instantly recognizable pattern of 7 bright stars in the northern sky, will look significantly different in 100,000 years than it does tonight. The stars at either end of the Dipper's bowl are moving in opposite directions across the sky, slowly pulling the familiar shape apart. The handle will curve differently. The bowl will be distorted. A person looking up 100,000 years from now, if humans or their descendants still exist and still look at the night sky, will see a different Big Dipper. Perhaps they will give it a different name. The most dramatic proper motion belongs to a faint star called Barnard's star, a small red dwarf approximately 6 light-years from the Sun, the second closest star system to Earth after the Alpha Centauri system. Barnard's star is moving across the sky at a rate of approximately 10.3 arcseconds per year, the fastest proper motion of any known star. This motion is invisible to the naked eye, but over a human lifetime, it moves by an amount just barely detectable with a good telescope and careful measurement. Over a century, it moves by about 17 arcminutes, roughly half the diameter of the full moon. Barnard's star is also approaching the solar system. In approximately 10,000 years, it will be the closest star to the Sun, passing within about 3.8 light-years. It will be the nearest stellar neighbor the solar system has had in millions of years, briefly brighter in the night sky than it is today, before continuing on its way, receding back into the distance over the following thousands of years. 10,000 years. That is within the span of recorded human history. The people who built the first cities in Mesopotamia, who domesticated the first crops, who painted the first cave paintings, were alive when Barnard's star was already measurably further from its current closest approach. The star's passage through the Sun's neighborhood spans a period that encompasses all of human civilization, and no one who lived through any of it noticed the star moving. Looking forward, the Sun's galactic journey continues. In 250 million years, the next galactic year, the solar system will have completed another circuit. In 5 billion years, roughly the remaining lifetime of the Sun on the main sequence, it will have completed approximately 20 more orbits. During those 5 billion years, the Sun will continue its slow bobbing above and below the galactic plane, will continue to be gently perturbed by the spiral arms it passes through, may continue its slow outward radial migration, if that process is real. The neighborhood of stars around the Sun will have changed completely. Most of the bright stars visible in tonight's sky are young, hot, short-lived objects that will have burned out long before the Sun's life ends. The stars that will neighbor the Sun 5 billion years from now have not yet been born. They are still molecular gas and clouds that have not yet begun to collapse. And in approximately 4 billion years, before the Sun's main sequence life ends, the Milky Way will begin its collision with the Andromeda Galaxy. The two largest galaxies in the local group, approaching each other at approximately 110 kilometers per second, will pass through each other, their stars streaming past one another in a gravitational ballet of extraordinary complexity and violence, their gas clouds colliding and triggering enormous starbursts, their dark matter halos interpenetrating and eventually merging into a single, larger system. In this collision, the Sun's orbit will be severely disrupted. The gravitational perturbations of billions of Andromeda stars passing through the Milky Way will scatter the Sun into a new orbit, possibly much larger, possibly extending far out into the halo of the merged galaxy. The Sun may end up in a completely different part of the galactic system than it occupies today, surrounded by a completely different population of neighboring stars. Its relationship to the galactic center fundamentally changed. But the Sun will survive, and the Earth, unless some close stellar encounter during the merger happens to disrupt the solar system, will survive with it. Life on Earth, if it still exists, will look up at a sky dramatically different from tonight's. The familiar pattern of the Milky Way will be gone, replaced by the bright, complex, irregular structure of two merging galaxies, the sky ablaze with the light of new star formation triggered by the collision. Strange and magnificent and utterly unlike anything any human eye has ever seen. All of that is 4 billion years away. And it begins in the most literal sense with the slow drift of the stars that is already underway, that has been underway since the Milky Way and Andromeda formed billions of years ago, that is simply the continuation of the galaxy's patient, imperceptible dance. The dance that you cannot see, the dance that is happening right now, all around you, in every direction, at every scale from the nearest star to the most distant galaxy. The universe is in motion, every part of it, always. You are moving with it at 230 kilometers per second around the galactic center, at 7 kilometers per second upward through the galactic plane, at the speed of the Earth's orbit around the Sun, at the speed of the Earth's rotation. All of these motions superimposed and adding up to a velocity through space that is relative to the cosmic microwave background. Approximately 600 kilometers per second. 600 kilometers per second. Right now, while you lie still, rest in that motion. Let it carry you. The galaxy knows where it's going. There is something happening right now that is unlike anything else in this chapter or in any other chapter we have explored tonight. Something that is not the movement of objects through space, not the drift of continents or the migration of stars or the erosion of mountains. Something more fundamental than any of those processes. Something that does not require force, does not require energy in the ordinary sense, does not have a source or a center, does not push anything or pull anything. Space itself is growing. Not space in some particular location. Not the space inside this room, or the space of the solar system, or the space of the Milky Way. Those regions are held together by gravity, bound into coherent structures that resist the expansion. But between the galaxy clusters, between the great gravitationally bound islands of the cosmic web, the space that separates them is stretching, growing, expanding in every direction simultaneously, carrying the galaxy clusters apart from each other like raisins in a rising loaf of bread, not moving through space, but being carried by the growth of space itself. This expansion is happening right now, at this very moment. The most distant galaxies we can observe are receding from us, their light redshifted by the stretching of the space through which it travels at speeds proportional to their distance. Galaxies at a distance of roughly 14 billion light years are receding at approximately the speed of light. Galaxies further than that are receding faster than light, not because they are moving through space faster than light, which special relativity forbids, but because there is so much space between us and them, and all of that space is growing, that the cumulative recession velocity exceeds the speed of light. Those galaxies are, in a real and observable sense, beyond our reach forever. Even light emitted by them today, the universe is growing, silently, continuously, in every direction at once. And it has been doing so since the Big Bang, 13.8 billion years ago, without pause, without slowing, and for the last approximately 5 billion years, with an acceleration driven by the dark energy that fills the vacuum of space. No instrument you own can detect the expansion directly. It is not a wind. It produces no sensation. It carries no information that can be intercepted on human scales. It is simply space becoming more space, on the only scales large enough to matter. The scales between galaxy clusters, where gravity has released its hold and dark energy reigns. For most of human history, the universe was assumed to be static, eternal, unchanging in its large-scale structure. The stars were fixed, or nearly so. The cosmos was a stage, perhaps infinite, perhaps bounded, but not growing or shrinking. Even Albert Einstein, when he developed the general theory of relativity in 1915 and found that his equations predicted a dynamic universe, one that must be either expanding or contracting, introduced an additional term, the cosmological constant, a kind of mathematical fudge factor, specifically to force his equations to produce a static universe. He found a dynamic universe so philosophically uncomfortable that he altered his most fundamental theory to avoid it. He later called this his greatest blunder, because the universe is not static. It is expanding, and the evidence came from an unlikely source: the careful measurement of the light from distant galaxies by an astronomer at the Mount Wilson Observatory in California. Edwin Hubble, working in the 1920s, made two discoveries that together transformed our understanding of the cosmos. The first was that the fuzzy patches of light, called nebulae, that astronomers have been debating for decades were not clouds of gas within the Milky Way, but were instead entirely separate galaxies, each one containing hundreds of billions of stars, each one separated from the Milky Way by distances measured in millions of light years. The universe was not the Milky Way. The Milky Way was one galaxy among an enormous number of them, scattered across a cosmos vastly larger than anyone had previously imagined. The second discovery followed from the first. When Hubble measured the spectra of these distant galaxies, he found that almost all of them showed a redshift. Their light was shifted toward longer, redder wavelengths, indicating that the source was receding. The galaxies were moving away from us, and, crucially, the further away a galaxy was, the faster it was receding. There was a linear relationship between distance and recession velocity. Double the distance, double the recession speed. This relationship is now called Hubble's law, and the constant of proportionality is the Hubble constant. The interpretation of Hubble's law is straightforward once you accept that space itself is expanding. In an expanding universe, every point recedes from every other point, with a recession velocity proportional to the distance between them. There is no center. There is no edge. Every galaxy is the center of its own observable universe, watching all the other galaxies recede in every direction. The universe is not expanding into anything. Space itself is simply growing, carrying everything within it apart from everything else. Hubble had discovered that the universe has a history, that it was smaller in the past, that running the expansion backward leads to a moment when everything was compressed into an extraordinarily hot, dense state. He had found the observational foundation of the Big Bang. For decades after Hubble's discovery, cosmologists assumed that the expansion of the universe was slowing down. This seemed reasonable. The universe contains matter, and matter has gravity, and gravity is attractive. The mutual gravitational attraction of all the matter in the universe should be pulling everything back together, decelerating the expansion, perhaps eventually halting it, and reversing it into a collapse. The question was not whether the expansion was decelerating, but how fast, and whether it would decelerate enough to eventually cause a big crunch. In 1998, two independent teams of astronomers, the HISE Supernova Search Team and the Supernova Cosmology Project, published results that overturned this expectation completely. They had been measuring the distances and recession velocities of type Ia supernovae, a particular class of stellar explosion that serves as a standard candle, a light source of known intrinsic brightness that allows distances to be calculated from observed brightness. By measuring supernovae at very large distances, they expected to find evidence of the deceleration. Instead, they found the opposite. The distant supernovae were fainter than expected. They were further away than the decelerating expansion model predicted. The expansion of the universe was not slowing down. It was speeding up. The universe is accelerating. Something is driving the expansion faster and faster with every passing billion years. That something, as we discuss in our journey through the Big Bang, is dark energy, a form of energy embedded in the vacuum of space itself, perfectly uniform, perfectly constant, filling every cubic centimeter of the universe with the same energy density regardless of how much space has expanded. Dark energy acts as a kind of anti-gravity on cosmological scales, a repulsive force that grows in total strength as the universe grows in volume. Because there is more space and therefore more dark energy, while the attractive gravity of matter weakens as matter becomes more dilute with expansion. For the first roughly 9 billion years of the universe's history, matter dominated. Gravity dominated. The expansion was decelerating, albeit slowly. But approximately 5 billion years ago, the universe crossed a threshold. The density of matter had been diluted by expansion to the point where the constant energy density of dark energy exceeded it. Dark energy took over, and since then, the expansion has been accelerating. The acceleration is not fast by any ordinary standard. The universe is not suddenly flying apart. The change in the expansion rate over a human lifetime is immeasurably small. But over billions of years, the cumulative effect is dramatic. The most distant galaxies we can currently observe will, over cosmic time, recede beyond our cosmic horizon, their light unable to reach us as the space between us expands faster than light can cross it. The observable universe is shrinking, not because space is contracting, but because the accelerating expansion is progressively placing more and more of the cosmos beyond the reach of our light. In the very distant future, trillions of years from now, the local group of galaxies, the gravitationally bound cluster containing the Milky Way, Andromeda, and their satellite galaxies, will be essentially alone in the observable universe. Every other galaxy cluster will have receded beyond the cosmic horizon. The night sky, for any astronomers alive at that time, will be almost perfectly dark. The galaxies of the local group will be visible, but beyond them, nothing. The universe will appear small and empty and isolated, giving no hint of the vast cosmos that existed in the past and that is still there, beyond the horizon, forever unreachable. The Hubble constant, the number that describes the current rate of the universe's expansion, is one of the most important and most carefully measured quantities in cosmology. It tells us how fast a galaxy at a given distance is receding due to the expansion of space, and from it we can calculate the age of the universe, the size of the observable universe, and many other fundamental properties of the cosmos. The current best measurements of the Hubble constant cluster around two values that stubbornly refuse to agree with each other. Measurements based on the cosmic microwave background, using the Planck satellite data, give a value of approximately 67 kilometers per second per megaparsec. Measurements based on the cosmic distance ladder, using Cepheid variable stars and type I supernovae to measure distances to nearby galaxies, give a value of approximately 73 kilometers per second per megaparsec. The discrepancy between these two values is now statistically significant enough that it is unlikely to be explained by random measurement error. Something is wrong, and we do not know what. This tension, called the Hubble tension, is one of the most active and most debated problems in modern cosmology. It may indicate that there is a systematic error in one or both sets of measurements, a subtle bias that has not yet been identified and corrected. It may indicate that the standard cosmological model, the Lambda-CDM model that assumes dark energy is a cosmological constant in cold dark matter, is incomplete and needs modification. It may indicate new physics, some ingredient or process that was active in the early universe and that has affected the expansion history in a way that the current model does not capture. The James Webb Space Telescope has been measuring Cepheid distances with unprecedented precision, and its results so far have confirmed the higher value for the distance ladder, making it less likely that the tension is due to systematic errors in the Cepheid measurements. The tension appears to be real. Its resolution, when it comes, may require a modification of our understanding of the universe's contents or its expansion history that will reshape cosmology significantly. The universe is expanding. We know this with certainty. The rate at which it is expanding we know with good, but imperfect precision. And somewhere in the small discrepancy between two careful measurements of that rate, there may be hiding a piece of physics that we do not yet understand. The expansion of the universe has a profound consequence for what we can and cannot observe. Because the universe has a finite age, and because light travels at a finite speed, there is a maximum distance from which light could have reached us since the Big Bang. This defines the observable universe, the sphere centered on Earth within which light has had time to travel to us. The observable universe has a radius of approximately 46 billion light years in all directions. This number is larger than you might expect given the age of the universe, roughly 13.8 billion years. If light has been traveling for 13.8 billion years, how can the edge of the observable universe be 46 billion light years away? The answer is that the universe has been expanding during all that time. The regions of space from which the oldest light was emitted were much closer to us when they emitted that light, but they have since been carried much further away by the expansion of space. The observable universe's radius reflects the current distance to those regions, not the distance at the time of emission. Within the observable universe, there are an estimated 2 trillion galaxies. Beyond the observable universe, in the unobservable regions from which light has not had time to reach us, there are almost certainly more. How many more depends on the geometry and size of the universe as a whole, which we do not know. The universe may be infinite, in which case there are infinitely many galaxies beyond our horizon. It may be finite but very large, with a size much greater than the observable portion. What we do know is that the observable universe is growing. Not because the expansion is bringing new regions into view. It is not. The accelerating expansion is actually reducing the rate at which new regions come into view. But because time is passing, and light that was emitted long ago from slightly more distant regions is only now arriving. Each year, a thin shell of new cosmic horizon is revealed to us. Light from regions we could not previously observe reaching our telescopes for the first time. And simultaneously, the most distant galaxies we currently observe are receding beyond our cosmic horizon, their future light unable to reach us. The observable universe is both gaining and losing members in a slow turnover that plays out over billions of years. We are in motion through a universe that is itself in motion, embedded in a galaxy that is drifting through a local group that is falling toward a larger structure, all of it embedded in the expanding fabric of space-time, carried apart from every other gravitationally unbound structure by the silent, forceless, ceaseless growth of space itself. You cannot feel the expansion. You cannot detect it with any sense or any instrument at human scales. But it is the largest, most pervasive, most consequential slow process in the universe. It is the context within which every other process we have discussed tonight occurs. The drifting continents and the eroding mountains and the evolving species and the cooling earth and the migrating stars are all happening within a universe that is on the largest scales, silently, perpetually, and now acceleratingly growing. Space is stretching around you. Right now, at every scale above the gravitationally bound. You cannot hear it. but is the oldest sound in the universe. The silence of space becoming more space. Rest in that silence. Of all the slow processes we have visited tonight, this is the slowest, the most patient, the most incomprehensibly drawn-out transformation that physics currently predicts will occur in the future of the universe. Black holes evaporate. Not quickly, not in any time frame that relates to anything we have discussed so far, not to the age of the universe, not to the predicted lifetime of the proton, not to any timescale that has any name in ordinary language. They evaporate on timescales so vast that describing them requires numbers with more digits than there are atoms in the observable universe. They evaporate one particle at a time, emitting a faint, cold radiation so dim that it would be invisible against any background that currently exists anywhere in the cosmos, losing mass so slowly that the word slowly does not come close to capturing the reality. But they evaporate. Stephen Hawking proved it, or rather derived it mathematically with extraordinary care in 1974, in what is widely regarded as one of the most beautiful and surprising results in the history of theoretical physics. A result that combined general relativity and quantum mechanics in a way that no one had previously managed, that revealed a deep and previously unsuspected connection between the physics of gravity and the physics of thermodynamics, and that showed that even the universe's most extreme objects, the black holes for which nothing, not even light, can escape, are not truly permanent. They are just very, very patient in their dying. A black hole is a region of space where gravity is so extreme that the escape velocity, the speed an object would need to travel to escape the gravitational pull, exceeds the speed of light. Since nothing can travel faster than light, nothing that enters a black hole can ever leave. Not matter, not radiation, not information of any kind, at least not according to classical general relativity. The boundary of this region is called the event horizon. It is not a physical surface. It has no material substance. It is simply a mathematical boundary, a threshold in space-time defined by the geometry of the gravitational field. Cross the event horizon moving inward and you can never return. From outside the event horizon, you cannot see what is inside. The black hole is black precisely because no light can escape from within the horizon to carry information to any outside observer. Black holes form when matter is compressed to sufficient density. The most common formation mechanism is the collapse of a massive star at the end of its life. When a star more than roughly 25 solar masses exhausts its nuclear fuel, the core collapses under gravity with nothing to stop it, and if the core is massive enough, it collapses past the neutron star threshold into a black hole. Stellar mass black holes typically range from a few to several tens of solar masses. At the centers of galaxies, including our own Milky Way, supermassive black holes lurk, containing millions to billions of solar masses, their origins still not fully understood, their influence on the galaxies around them profound and far-reaching. The supermassive black hole at the center of the Milky Way, Sagittarius A*, contains approximately 4 million solar masses. The supermassive black hole at the center of the galaxy M87, famously imaged by the Event Horizon Telescope in 2019, contains approximately 6.5 billion solar masses. These objects, from the stellar mass remnants of dead stars to the billion solar mass giants at galactic centers, are the most extreme concentrations of mass in the universe. They distort space-time so severely that time itself slows near them and stops at the event horizon. They are, by any measure, the most permanent-seeming objects the universe currently contains. And they are evaporating. The derivation of black hole evaporation begins with a property of the quantum vacuum that we touched on in our discussion of the Big Bang. The vacuum is not empty. Even in a perfect vacuum, in a region of space containing no particles and no radiation, quantum field theory predicts that the fields that permeate space are in a state of constant fluctuation. Virtual particles, pairs of matter and antimatter, constantly flicker into existence and annihilate each other in intervals so brief that they violate no conservation law in any measurable way. In flat space-time, far from any gravitational field, these virtual particle pairs always annihilate. They appear together, briefly exist, and destroy each other, leaving no net change in the state of the vacuum. They are a kind of quantum foam, constantly roiling beneath the apparent calm of empty space, but producing no permanent particles and no net energy flow. Near a black hole's event horizon, something different happens. The event horizon creates a sharp boundary in space-time, a surface on one side of which escape is possible and on the other side of which it is not. When a virtual particle pair appears very close to the event horizon, it is possible for one particle of the pair to fall inside the horizon before the pair can annihilate, while the other escapes to infinity. The particle that escapes carries positive energy and becomes a real particle, emitted as radiation from the vicinity of the black hole. The particle that falls and carries negative energy from the perspective of an outside observer, effectively reducing the black hole's mass. The net result is that the black hole slowly loses mass, emitting a steady, faint stream of thermal radiation. This is Hawking radiation. It is named for Stephen Hawking, who derived it in 1974 using a calculation that combined the quantum field theory of particles in curved spacetime with the thermodynamics of black holes. The calculation was extraordinarily subtle and technically demanding, and its result was a complete surprise even to Hawking himself. The temperature of the Hawking radiation is inversely proportional to the mass of the black hole. A more massive black hole emits colder Hawking radiation. The formula gives a temperature of approximately 60 nanokelvin for a black hole of 1 solar mass. 60 nanokelvin is 60 billionths of a degree above absolute zero. It is colder than any temperature that currently exists naturally anywhere in the observable universe. The cosmic microwave background at 2.7 degrees Kelvin is roughly 45 million times warmer than the Hawking radiation of solar mass black hole. This means that a stellar mass black hole in the current universe is not evaporating in any net sense. It is absorbing CMB photons at a rate far exceeding the rate at which it emits Hawking radiation. It is actually gaining mass very slowly from the ambient radiation of the universe. Only when the universe has cooled sufficiently, when the CMB temperature has dropped below the Hawking temperature of the black hole, will the black hole begin to lose mass in net terms. For a solar mass black hole, this will not happen for approximately 10 to the 19th years, roughly 1 billion times the current age of the universe. The universe must first cool down around the black hole before the black hole can begin to evaporate. And then the evaporation will begin, slowly, particle by particle. The time it takes a black hole to fully evaporate through Hawking radiation depends on its mass, and the dependence is steep. The evaporation time scales as the cube of the mass. Double the mass of the black hole, and its evaporation time increases by a factor of 8. A black hole 10 times more massive takes 1,000 times longer to evaporate. For a black hole of 1 solar mass, the evaporation time is approximately 2 times 10 to the 67 years, 2 followed by 67 zeros. This number is so large that it renders every other timescale we have discussed tonight, the proton lifetime at 10 to the 34 years, the age of the universe at 10 to the 10 years, negligibly small by comparison. The evaporation time of a solar mass black hole is 10 to the 57 times longer than the current age of the universe. For the supermassive black holes at the centers of galaxies, the evaporation times are longer still. A black hole of 1 billion solar masses, typical of the largest supermassive black holes we observe, has an evaporation time of approximately 10 to the 83 years. 10 to the 83. If you try to write this number in standard notation, you would need a piece of paper longer than the observable universe to fit all the zeros. And for the most massive black holes in the universe, the ultramassive black holes of tens of billions of solar masses found in the centers of the largest elliptical galaxies, the evaporation time approaches 10 to the 100 years or beyond. A 1 followed by 100 zeros. A googol years. These timescales are not merely large. They are large in a way that defeats every analogy and every intuition. They are large in the way that infinity feels large, not infinite themselves, but pointing in that direction with a gesture so extreme that the distinction between them and infinity seems academic from any human vantage point. And yet, the physics insists these times are finite. The evaporation will complete. Every black hole in the universe, from the smallest stellar remnant to the most massive galactic titan, will eventually, one Hawking photon at a time, return all of its mass to the universe as radiation. The evaporation of a black hole is not uniform throughout its lifetime. For most of its existence, the evaporation is so slow as to be completely undetectable by any instrument conceivable. The black hole sits in the cooling universe, absorbing the diminishing ambient radiation and slowly, with geological patience, losing mass to Hawking radiation. For the first 99.999999% or more of its evaporation time, nothing dramatic happens. The black hole simply shrinks, imperceptibly, epoch by epoch, as the universe cools around it and time accumulates in quantities that have no name. But as the black hole's mass decreases, its temperature increases. And as its temperature increases, it radiates more intensely. The evaporation accelerates. The black hole gets smaller, hotter, and more radiant. The process feeds on itself. Smaller means hotter. Hotter means faster evaporation. Faster evaporation means smaller still. In the final moments of a black hole's life, this runaway process produces a dramatic crescendo. In the last fraction of a second of its existence, as the black hole's mass approaches the Planck mass, approximately 22 micrograms, a tiny but finite amount of matter comparable to a large biological cell, the temperature of the Hawking radiation reaches the Planck temperature, approximately 10 to the 32 degrees Kelvin. The most extreme temperature physics currently allows description of. The black hole emits a final burst of radiation, a flash of extraordinarily energetic particles and photons, and then it is gone. The entire mass of what was once perhaps a stellar mass black hole of several solar masses, or perhaps a supermassive black hole of billions of solar masses, has been converted entirely to radiation, to photons and other particles streaming outward in a final explosion from the point where the black hole's event horizon used to be. There is nothing left, no remnant, no scar in space-time, just the expanding sphere of radiation, cooling and redshifting as it travels outward into the vast, dark, nearly empty future universe. It will happen to every black hole that currently exists. It will happen to Sagittarius A*, the 4 million solar mass black hole at the center of our galaxy. Not for approximately 10 to the 83rd years, but it will happen. It will happen to the black holes of the largest galaxy clusters, the ultramassive objects of tens of billions of solar masses. Not for approximately 10 to the 106th years, but it will happen. After the last black hole has evaporated, the universe will contain no more black holes, no more large concentrations of mass of any kind, assuming protons have decayed by then. Only a diffuse, cold, endlessly expanding sea of photons and neutrinos and electrons and positrons, all of them cooling and redshifting and spreading through a space that continues to grow, approaching but never quite reaching absolute zero, approaching but never quite reaching perfect equilibrium. Hawking radiation raises one of the deepest and most troubling puzzles in all of theoretical physics, a puzzle that has occupied the greatest minds in the field for 50 years and has not yet been definitively resolved. Quantum mechanics has a fundamental principle called unitarity. It states that information is conserved. The quantum state of a system at any moment in time determines its state at all future times, and in principle the past state can be reconstructed from any future state. Information is never lost. It is always, in some form, preserved in the quantum state of a universe. But black holes seem to violate this principle. When matter falls into a black hole, the information about its detailed quantum state, which particles it was made of, what their spins and momenta and other quantum numbers were, appears to be lost. The black hole erases the information, replacing the complex quantum state of the infalling matter with a featureless description characterized only by the black hole's mass, electric charge, and angular momentum. And when the black hole evaporates through Hawking radiation, the radiation appears to be purely thermal, random, carrying no information about what fell in. The information appears to be permanently destroyed. This is the black hole information paradox, and it sits at the junction of quantum mechanics and general relativity, precisely the place where our current understanding of physics is most incomplete, where the two great theories of modern physics are most deeply in tension with each other. Various resolutions have been proposed. Hawking himself initially believed that information was genuinely lost, that black holes represented a fundamental exception to the principle of unitarity, a place where quantum mechanics broke down. He later changed his mind, conceding in 2004 that information is probably preserved, though the mechanism by which it escapes remains unclear. The most influential recent approach to the paradox involves a conjecture called black hole complementarity and its more recent descendant, the firewall paradox. The broad idea is that the information that falls into a black hole is not lost, but is encoded in the Hawking radiation in an extraordinarily scrambled, encrypted form. That an observer outside the black hole sees the information gradually leak out in the Hawking radiation, while an observer falling into the black hole sees nothing unusual at the horizon. The two descriptions are complementary, valid for different observers, and the apparent contradiction is resolved by the fact that no single observer can access both descriptions simultaneously. Whether this resolution is correct, and precisely how the information is encoded in the Hawking radiation, remains an open and intensely active area of research. The information paradox is not solved. It is one of the places where theoretical physics is most alive, most creative, most genuinely uncertain about the deepest nature of reality. What we can say with confidence is this: whatever the ultimate resolution of the information paradox, whatever the mechanism by which information is preserved or the way in which the paradox is dissolved, it will require a deeper understanding of quantum gravity than we currently possess. It will require the theory that reconciles quantum mechanics and general relativity, the theory that has been sought for a century and that remains the greatest outstanding challenge in fundamental physics. The black hole, in its slow, patient, almost eternal evaporation, is asking us a question that we cannot yet answer. A question about the deepest nature of information, of time, of the relationship between the quantum and the gravitational. It will be waiting for a very long time for our answer. It has time, more time than we can imagine. Every star you have ever seen will go out. Not tonight, not in your lifetime, or in the lifetime of any civilization that has ever existed or that could plausibly exist on any timescale we ordinarily think about. The sun has approximately 5 billion years of hydrogen left to burn. The dimmest, most frugal red dwarf stars, the ones so small and so cool that they burn their fuel at the most miserly possible rate, have trillions of years ahead of them. On any human timescale, the stars are effectively eternal. They have been burning since before the Earth existed, and they will be burning long after the last trace of our civilization has been erased from the geological record. But they are burning through finite fuel. Every star is a controlled nuclear explosion, sustained by the inward pull of gravity balanced against the outward pressure of the energy released by fusion in the core. And every nuclear reaction consumes fuel. The hydrogen becomes helium. The helium eventually becomes carbon and oxygen. The carbon and oxygen in the most massive stars become heavier elements still, all the way up to iron, beyond which fusion no longer releases energy. And when the fuel runs out, the fire goes out. The stars are temporary. All of them. Every point of light in the night sky. Every star in every galaxy in the observable universe. Every fire that is burning anywhere in the cosmos is burning through fuel that will eventually be exhausted. The universe began its stellar era with a finite supply of hydrogen, forged in the first 3 minutes after the Big Bang. That supply is being consumed, one fusion reaction at a time, in the cores of 100 billion trillion stars. And when it is gone, when the last star has fused its last hydrogen nucleus into helium and then swelled and cooled and faded, the universe will be dark in a way it has not been since the cosmic dark ages, hundreds of millions of years before the first star ignited. That darkness is coming, slowly, on a timescale of trillions of years. But it is as physically inevitable as the sunrise is predictable. The stars are going out, one by one, over the deepest future of the universe. Stars do not simply vanish when they die. They leave remnants, and the nature of the remnant depends on the mass of the original star. Understanding the stellar graveyard, the collection of dead stars that accumulates as the universe ages, is essential to understanding what the universe will look like in the deep future after the last star has burned out. The least massive stars, the red dwarfs with masses below approximately 40% of the sun's mass, burn their hydrogen so slowly and so completely that they consume essentially all of their fuel over their extraordinarily long lifetimes. When a red dwarf finally exhausts its hydrogen, it does not swell into a red giant the way larger stars do. It simply cools and fades, contracting into a small, dense, inert ball of helium. This remnant is called a white dwarf, though the white dwarfs produced by red dwarfs will be helium white dwarfs, slightly different from the more common carbon-oxygen white dwarfs produced by sun-like stars. Eventually, over immense timescales, these white dwarfs will cool further, fading through yellow and orange and red to a deep, invisible infrared glow, and finally becoming what astronomers call black dwarfs, cold, dark, inert balls of electron-to-generate matter drifting through the dark universe. Stars like the Sun, in the middle mass range between roughly 40% and 8 times the Sun's mass, die more dramatically. After burning their core hydrogen, they expand into red giants, fusing helium in a shell around the exhausted core, and then in the core itself, producing carbon and oxygen. The outer layers are gradually expelled as a beautiful expanding shell of gas called a planetary nebula, illuminated by the hot remnant core within it. The remnant core becomes a white dwarf, composed primarily of carbon and oxygen, roughly the size of the Earth, but containing roughly the mass of the Sun. This white dwarf will cool over billions and then trillions of years, eventually becoming a cold, dark black dwarf. The most massive stars, those above roughly 8 solar masses, end their lives in spectacular core collapse supernovae that leave behind either neutron stars or black holes. Neutron stars are extraordinarily dense objects, comparable in mass to the Sun, but only about 20 kilometers in diameter, composed primarily of neutrons packed together at densities approaching those of atomic nuclei. They cool over millions and billions of years, eventually becoming cold, dark, inert neutron stars drifting through the universe. Black holes, as we discussed in the previous chapter, will eventually evaporate through Hawking radiation, but on timescales so vast they need not concern us here. The universe of the deep future, after the last star has burned out, will be populated by the remnants of the stellar era. Black dwarfs and neutron stars and black holes, cold and dark and silent, drifting through an expanding universe in which the distances between them grow ever larger as dark energy continues its patient work of stretching space. The stellar graveyard is already being filled. Every star that has ever died has left a remnant. The white dwarfs cooling in the halos of galaxies today, the neutron stars spinning in the planes of galaxies, the black holes at galactic centers, all of them are the advanced scouts of the long dark future that awaits the universe after the last fire goes out. The story of the fading stars is not told in a single chapter. It is told in a sequence of chapters of vastly different lengths, the longest of which has not yet begun. We are currently living in what cosmologists call the stelliferous era, the age of stars. This era began with the formation of the first stars a few 100 million years after the Big Bang, and will end when the last star burns out. Estimates of when this era will end depend on the assumed star formation rate, and on which stars we count as part of the era. The most optimistic estimates, accounting for the fact that the smallest red dwarf stars will still be burning 10 or even 100 trillion years from now, place the end of the stelliferous era at approximately 10 to the 14 years in the future. 10 to the 14 years. 100 trillion years. This is roughly 7,000 times the current age of the universe. If the current age of the universe were a single day, the stelliferous era would last for 20 years. We are, in that analogy, in the first few hours of the first day. During most of this remaining time, the universe will be dominated by red dwarfs. The large, bright stars, the ones that light up the night sky and that we most readily associate with the word star, are burning through their fuel rapidly. The sun will burn out in 5 billion years. A star of 10 solar masses will burn out in tens of millions of years. A star of 50 solar masses will burn out in a few million years. These bright, massive stars are already dying throughout the universe, their brief, brilliant lives ending in supernovae that scatter their synthesized heavy elements into the interstellar medium. But the red dwarfs, the dim, cool, small stars that make up roughly 75% of all stars in the Milky Way, are extraordinarily long-lived. A red dwarf of half a solar mass will live for approximately 50 to 60 billion years, 4 to 5 times longer than the current age of the universe. A red dwarf of 1/10 of a solar mass will live for perhaps 6 to 12 trillion years, 1,000 times the current age of the universe. The very smallest red dwarfs, those of about 8% of solar mass, teetering on the boundary of hydrogen fusion, may live for 10 trillion years or more. For most of the stelliferous era, the universe will be a place of dim, red, patient stars. The brilliant blue giants and yellow, sun-like stars will be long gone. The galaxy clusters will have merged and settled into enormous, diffuse elliptical assemblages of dim red and orange stars. The night sky, for any observers alive in the middle of the stelliferous era, would be profoundly different from tonight's. Dimmer, redder, quieter, fewer supernovae lighting the sky, fewer new stars forming, as the gas in the galaxies has been progressively consumed and the remaining red dwarfs slowly exhausted. And then, one by one, over the last several trillion years of the era, even the red dwarfs will fade. The smallest will go last. The universe's last star, perhaps a red dwarf of 8 or 9% of solar mass, will fuse its last hydrogen nucleus in a helium somewhere in the range of 10 to the 13 or 10 to the 14 years from now, cool and fade to a black dwarf, and the stelliferous era will be over. The last fire will go out, and the universe will be dark again. I want to spend a moment imagining the last star, not because we can know anything specific about it, not its location or its mass, or whether it was born in a spiral galaxy or an elliptical one, or some merged remnant structure that has no name in our current taxonomy. But because the idea of it, the last fire in the universe, the final act of the 10 trillion year drama of stellar nucleosynthesis, deserves a moment of attention. The last star will be a red dwarf. Almost certainly, the statistics of stellar masses make this essentially guaranteed. It will be small, perhaps 10% of the sun's mass. It will be dim, its luminosity perhaps a 10,000th of the sun's, glowing a deep, cool red at a surface temperature of perhaps 2,500 degrees. It will have been burning for perhaps 10 trillion years when it finally exhausts its fuel, having been born in a universe already ancient beyond any timescale we currently use. When it formed, the universe around it will have already been dark for many trillions of years. The bright stars of the early universe, the sun-like stars, and the massive blue giants will have been gone for so long that their absence is the only condition the universe has known for most of its history. The last star will have formed in a universe that was already quiet, already dominated by the dim red light of the penultimate stellar generation, already more graveyard than nursery. And when it fades, when the last hydrogen in its core fuses into helium and the energy output drops and the star begins its long, slow cooling, there will be no replacement. The interstellar gas that would be needed to form new stars will have been consumed, used up in previous generations of star formation, or dispersed too thinly by the expansion of space to ever collapse into new stars under any realistic scenario. The last star will die without a successor. The universe that watches it fade, if anything in that universe can be said to watch, will be a cold, dark, ancient place. The temperature of the cosmic background radiation will have dropped to perhaps 10 to the negative 30 degrees above absolute zero, so close to absolute zero that the difference is meaningless for any practical purpose. The black holes will still be there, slowly evaporating, but they will not yet have completed their evaporation by the time the last star goes out. The black dwarfs and neutron stars will be there, cold and dark and silent. And the last red dwarf will cool and join them. And then, silence. The kind of silence that the universe has not known since the Dark Ages for 100 million years into its life, when it was young and the first stars had not yet ignited. A silence that this time will not be broken. A silence measured not in millions of years, but in trillions, and then quadrillions, and then the incomprehensible timescales of the black hole era and the dark era beyond. Every fire that ever burned in the universe began with hydrogen forged in the first 3 minutes after the Big Bang. Every star that ever shone drew on that primordial fuel. And when the last red dwarf goes out, the last of that fuel will have been spent. The universe will have used up the inheritance of its own beginning. It is, in the deepest sense, the end of an era. The end of the era of fire. And what comes after is something the universe has never been before. Cold, dark, patient beyond any word. After the last star goes out, the universe enters what cosmologists call the degenerate era, the era of stellar remnants, of black dwarfs and neutron stars and black holes, drifting through an expanding, cooling, darkening universe. This era will last for an extraordinarily long time, dwarfing even the stelliferous era that preceded it. The black holes will evaporate over timescales of 10 to the 67 to 10 to the 100 years and beyond. The black dwarfs, if protons do not decay, will persist essentially forever, slowly growing colder and denser, their electron-degenerate matter approaching the coldest possible configuration of matter. The neutron stars will cool similarly, their surfaces approaching absolute zero over trillions of years. In this dark era, the universe will be inhabited by ghosts, the cold remnants of stars that burned and died, drifting in the dark, separated by ever-growing distances as space continues to expand. Occasionally, over immense timescales, two black dwarfs or neutron stars will drift close enough to interact gravitationally, merging in a brief, violent event that releases energy and then is swallowed again by the dark. Occasionally, a cold remnant will be scattered by a gravitational encounter into an orbit that takes it close to a black hole, and it will be absorbed. These events will be extraordinarily rare, separated by timescales of billions and trillions of years. The universe of the degenerate era will be, by any human standard, inconceivably cold, inconceivably dark, and inconceivably lonely. The distances between any two objects will be measured in numbers that have no names. The energy available to drive any process will be vanishingly small. The universe will be approaching, but not yet reaching, the final state that thermodynamics predicts for any closed system left to itself for long enough. The heat death, which is where we will go in our final chapter. But first, let the stars fade. Let the last red dwarf cool in your imagination. Let the universe go dark around it, slowly, over trillions of years, the way the sky darkens after sunset. Not all at once, but gradually, the brightest lights holding on longest against the encroaching dark, until finally even they are gone and the darkness is complete. The stars were magnificent, every one of them. They burned and they shone, and they forged the elements of which you are made, and they died, and their deaths seeded the universe with the possibility of planets and chemistry and life. They deserved their trillions of years. They earned the darkness that follows them. Let the last one go gently. It has burned long enough. There is a law of physics that is, in certain moods, the most melancholy thing in all of science. The second law of thermodynamics. It states, in its simplest formulation, that in any closed system, entropy always increases or remains the same. It never decreases. Entropy is a measure of disorder, of a number of possible microscopic arrangements consistent with a given macroscopic state. A hot cup of coffee cooling in a cool room is increasing in entropy. The heat spreads from the cup into the room until everything is at the same temperature, a state of maximum entropy for that system. You never see a cool cup of coffee spontaneously growing hot while the room cools. The process only goes one way. The universe as a whole is a closed system, and its entropy has been increasing since the Big Bang. Every process, every event, every transformation of energy from one form to another increases the total entropy of a universe by some amount. The burning of stars increases entropy. The evaporation of black holes increases entropy. The cooling of white dwarfs increases entropy. Every single thing that happens in the universe, from the fusion of hydrogen in a stellar core to the firing of a neuron in your brain, contributes to the steady, relentless, universal increase in disorder. And the end point of this process, the state of maximum entropy toward which the entire future of the universe is inexorably tending, is called the heat death. A state in which all energy has been uniformly distributed throughout the universe, in which there are no remaining temperature differences to drive any process, in which no work can be done anywhere, in which nothing further can happen. Not an explosion, not a collapse, not a dramatic ending of any kind, just a stillness, a final, absolute, universal stillness in which the universe has reached the equilibrium it has been approaching since the beginning, in which every gradient has been smoothed, every difference resolved, every pocket of order dissolved back into the featureless uniformity from which everything began. The heat death is the slowest possible ending, the most patient of all endings. It does not arrive in a moment. It approaches asymptotically over timescales beyond any we have discussed tonight, each step smaller than the last, each moment closer to equilibrium, but never quite there, the universe forever approaching, but in theory never quite reaching the absolute stillness of maximum entropy. The heat death is not darkness in the way we ordinarily imagine darkness. It is not a universe that was lit and then went dark the way a candle goes out. It is a universe that has become uniform, uniformly cold, uniformly dim, uniformly disordered, after the last black hole has evaporated, which occurs on timescales of roughly 10 to the 100 years for the largest black holes. The universe will contain no large concentrations of mass or energy anywhere. The protons, if they have decayed by then, will be gone. The electrons and positrons that remain will be drifting through space at extremely low densities, occasionally meeting and annihilating into photons, those photons spreading outward and redshifting as the universe continues to expand. The photons themselves, the radiation from every source that has ever existed in the universe, from the Big Bang to the last black hole evaporation, are still present, but are spread across an unimaginably vast volume of space, each one carrying an unimaginably small amount of energy, their wavelengths stretched by the expansion of the universe to lengths that dwarf any scale we can describe. The temperature of this radiation approaches, but does not reach absolute zero, 10 to the negative 30 degrees, 10 to the negative 60 degrees, asymptotically close to nothing, but never nothing. There are no structures, no atoms, if protons have decayed, no molecules, no chemistry, no biology, no information processing of any complexity. There is nothing to distinguish one region of space from another in any significant way. The universe has become the flattest, smoothest, most uniform thing imaginable. Not because something compressed it into uniformity, but because everything that was ordered has had the time to dissolve into disorder. The second law of thermodynamics has run its course, all the way to the end. Every difference that was created at the Big Bang, every temperature gradient, every concentration of mass, every ordered structure from the first stars to the last black holes, has been dissolved by the patient, relentless operation of entropy over timescales that make the current age of the universe negligibly small. The universe began in a state of low entropy. The Big Bang produced an extraordinarily ordered initial condition, hot and dense and uniform in large scale, but carrying the seeds of all future structure in its tiny quantum fluctuations. Everything since then has been the unfolding of that initial order, the slow transformation of the Big Bang's inheritance into the maximum disorder of the heat death. 13 billion years of history so far. The stars and galaxies and nebulae and planets and oceans and mountains and forests and cities and thoughts, all of it the universe, spinning the order it was born with like a fire slowly consuming the fuel that was laid for it at the beginning. The fire is beautiful, extraordinarily beautiful, and has been burning for a very long time. But the fuel is finite, and the heat death is where the last of it is finally spent. After the heat death, what? This is a question that physics cannot currently answer with any confidence. The heat death, if it is truly the final state, is not an ending that leads to anything else. It is simply the final condition, persisting forever in the expanding, cooling, featureless void. Nothing happens in the heat death because there is no free energy to drive any process. Time continues to pass, but nothing changes. The universe is, in the most complete sense, done. Some theorists have speculated that the heat death is not truly final, that even in a universe at maximum entropy, quantum fluctuations could, given infinite time, spontaneously produce ordered structures. A single particle, a single atom. Eventually, over timescales so vast they make the black hole evaporation timescales look like instants. Even a Boltzmann brain, a hypothetical spontaneously assembled self-aware structure arising from random quantum fluctuations in the void. Or even at the very extreme of speculation, a new low-entropy state that seeds a new expansion, a new Big Bang, a new universe. These speculations are not science in the ordinary sense. They are thought experiments at the very edge of what physics can say anything meaningful about. The timescales involved, typically cited as 10 to the 10 to the 10 to the some large number of years, are so far beyond any physical process that the word time barely retains its meaning. Whether these speculations are meaningful physics or philosophical fantasy is itself a contested question. What we can say with confidence is this: the universe we inhabit, with its stars and galaxies and planets and life and consciousness, is a temporary phenomenon, extraordinarily long-lived by any human standard, rich beyond any full accounting, beautiful in ways that will never be completely described, but temporary, bounded on both ends by states of near uniformity, by the hot, dense plasma of the Big Bang and the cold, dilute void of the heat death, with 13 billion years of extraordinary, improbable, structured complexity in between. We are in the middle of that complexity. We are among its most intricate and self-aware expressions. And tonight, we have spent 3 hours exploring the edges of it, the slowest processes at the boundary between the ordered and the entropic, between the structured and the dissolving, between the alive and the eventual still. We have come to the end of our long, slow journey tonight. We began with the ground moving beneath your feet at 2 centimeters per year. We ended with the universe approaching a stillness so absolute and so patient that no word in any human language comes close to describing it. Between those 2 endpoints, we traveled through the death of mountains and the branching of species and the cooling of the Earth's interior and the possible dissolution of matter itself and the migration of stars through the slow dance of the galaxy and the silent stretching of space and the hawking evaporation of the universe's last great structures and the fading of the last fire in the cosmos. All of it slow, all of it invisible on any human timescale, all of it happening right now, tonight, in the dark, whether we attend to it or not. I want to close with something that I've been thinking about throughout this journey, something about what slowness teaches, about what it means to inhabit, briefly and improbably, the middle of a universe that operates on timescales so vast they defeat every ordinary intuition. There's a temptation, when confronted with deep time, to feel diminished, to feel that the brevity of human life, measured against the billions of years of geological history beneath your feet and the trillions of years of stellar future above your head, makes that life somehow negligible. A rounding error in the cosmic account, too brief to matter, too small to count. I want to suggest the opposite. The brevity of human life is not its tragedy. It is its specific character. The fact that you have perhaps 70 or 80 or 90 years, and not trillions, means that every one of those years is dense with unrepeatable particularity. The people you love, the specific quality of light on a specific afternoon, the taste of a specific meal, the sound of a specific voice. These things are not available to the red dwarf that will be burning 10 trillion years from now. They are not available to the black dwarf that will be drifting in the dark 10 to the 37th years hence. They are available only to creatures like us, brief and warm and present, embedded in the rich middle of cosmic time. The slow processes we have discussed tonight, the drifting continents and the fading stars and the cooling core of the world, give us the context in which our brevity becomes legible. Against the backdrop of geological time, a human life is a flash of light. But a flash of light is, in its own way, more vivid than the long, slow dimming of a red dwarf. More information dense, more present, more alive to the specific texture of a specific moment. You are brief. You are temporary. You are made of matter that was once part of stars and will one day be part of something else entirely. And right now, tonight, you are here, awake or drifting towards sleep, breathing air that ancient oceans exhaled, warmed by a star whose hydrogen was forged in the first 3 minutes of the universe, resting on a planet whose surface is moving grain by grain toward the sea. The slowness of the universe is not indifference. It is simply the universe operating on its own schedule, at its own pace, with the patience that only something of its size and age can sustain. And your presence within it, brief as it is not an accident or an irrelevance. It is the universe doing something it does rarely and with great difficulty, becoming aware of itself, thinking its own thoughts, feeling its own feelings, asking its own questions. You're the universe's way of noticing that it is slow. That is not a small thing. Let me close by bringing the slowness back to the immediate, to the room you are in, to this moment. Right now, the continental plate beneath you is moving 2 centimeters per year, one direction or another, depending on where in the world you are, but moving, silently, powerfully without pause. Right now, somewhere in the world, a grain of rock is separating from a cliff face and beginning the 100 million year journey to the sea. Right now, in some population of organisms somewhere on Earth, a mutation is occurring that will, over thousands of generations, become fixed in the population and contribute to the slow, invisible process of evolution that has been running for 4 billion years. Right now, the Earth's core is slightly cooler than it was a year ago, by an amount no instrument can measure. But cooler. Right now, in a tank of ultra-pure water deep under a mountain in Japan, 50,000 tons of protons are being watched by 11,000 glass eyes, waiting in silence for a flash that may never come. Right now, the sun is completing another tiny arc of its 250 million year orbit around the galactic center, carrying the solar system, carrying the Earth, carrying you at 230 kilometers per second through the patient dark of the galaxy. Right now, the most distant galaxies in the observable universe are receding, carried by the expansion of space, one by one, beyond our cosmic horizon, their light unable to ever reach us again. Right now, the supermassive black hole at the center of the Milky Way is emitting Hawking radiation at a temperature of 60 nanokelvin, losing mass at a rate so infinitesimal that it will take 10 to the 83 years to evaporate completely. Right now, the red dwarf stars at the edge of the Milky Way are burning their hydrogen at the most careful, frugal, patient rate that nuclear physics permits, preparing for lifetimes of 10 trillion years. All of it happening right now, in the dark, while you breathe, while your heart beats, while your thoughts form and dissolve and reform in the warm, brief, improbable miracle of a living mind. The universe is slow. It has always been slow. It will always be slow. And you, in your particular brevity, in your specific and unrepeatable moment of being alive, are the fastest thing in it. The most present, the most awake, the most here. Let that be enough. Let the slow world turn beneath you. Let the stars drift above you. Let the continents carry you 2 centimeters at a time through the long, patient history of a world that was here before you and will be here long after, that does not need you to witness it, but is richer for the fact that something briefly does. You witnessed it tonight. For 3 hours, you let the universe be slow around you. That is a rare and quiet kind of attention. The slow world thanks you for it. Sleep well.